astronauts to the moon.
Ignition sequence start. 3, 2, 1.
Houston, we have a problem.
Liftoff. We have a liftoff. We copy you on the ground. You got a bunch of guys about to turn blue.
What you're seeing here is a mirage.
What's up, everyone? What's going on, everyone? It's Jeranism, back with another live video for you. Tonight, a conversation with Charles, Flat Earth Math. So, Charles, how are you?
I am doing quite well. How are you, sir?
Very good, thank you. Thank you for joining me for what should be another fun little conversation. The reason behind this little get-together was my recent video that was 5 facts about the Earth that we didn't learn in school. Charles had made a comment pretty early when that video came out, I think the same day, that basically said, well, why don't you tell us what you said, Charles?
Well, basically, the comment started, argument from incredulity is not a, is a logical fallacy. And it just seemed that the 5 things that you had in your video, they really dealt with things that were hard to believe, therefore they're fake. So,
gotcha.
So I just got a few things to say about each of them.
So when you talk about an argument from incredulity, what is like the definition of incredulity? And I'll look that up because wouldn't the synonym of that be skepticism?
Skepticism is great. Healthy skepticism is great. But when you're talking about something that we don't understand, or like, let's say there is somebody who is an expert at it, and then there's somebody who's a newbie. Well, just about any facet of that to the newbie is just going to be incredible. Like, for example, the example I give is a V8 engine. If you are accelerating on the freeway and you go 5,000 RPM with a V8 engine, which happens every day, the cylinders are actually firing 333 times per second. And that number is just, I mean, like, I can't imagine all those machines, 333 times per second is a huge, huge number. It's hard for me to believe. Well, therefore it's fake, Well,
the difference would be that you could, if you had a question about that, ask someone to show you I'm sure they have a video that's in slow motion that could prove it for you. So yes. I think skepticism is healthy because you're going to say, I don't know, that sounds a little bit unbelievable to me. And then you're going to get shown that your unbelief was incorrectly justified. So where the difference between this and that is when somebody tells me that we are going around the Great Attractor, which is some quintillion or sextillion miles wide. It's a
gajillion miles away.
Yeah. And I say, that I have a hard time believing that. The difference here is I'm not presented with proof. What I'm given is mathematics. I'm given numbers basically saying, well, because we believe all of this stuff, it must be true. We have never observed it, but it must be. And so that's the difference between an argument from incredulity, in my opinion, that I have no problem with anybody's argument if they're saying, well, I don't believe it because it sounds simply unbelievable. But if those things are followed by evidence, then that person quickly learns that they shouldn't have doubted that. So,
and something I've always told you, Jaron, is that you have very good questions. And that is something I really, really want to encourage you and anyone else in the Flat Earth debate is just, keep having those great questions. And then what I'm going to do on my side is I'm going to try my best to try to answer them, or at least try to point you in the right direction. But what I see happening is sometimes people will have a good question, but then they can't think off the top of their head what the answer would be. Therefore they draw the wrong conclusion. So,
right. Another question for you, just something I'm wondering. Did you happen to catch the Red's Rhetoric's debunking of the Globebusters show?
No, I did not, and I actually chose not to. What I was doing is I was listening to the Globebusters show and not the Red's Rhetoric show. I'm very fond of a number of people in that crew for some of their technical stuff, like the record video launches that Red's done. But I am not fond of their approach to the Flat Earth debate, and I mean no disrespect to anybody, but their approach to the Flat Earth debate, from what I've seen, is insult, insult, insult. You're stupid. You're an idiot. Lots of profanity. I mean, not that I'm a prude. I mean, I could curse like a sailor. But that doesn't help the argument. profanity and insults don't help the discussion. So I watched your show. I didn't watch their show.
Okay. Yeah, I was just wondering, and I see it the same way. And again, can curse like a sailor myself, but I think that there's a time and a place for everything. And, that's certainly not it when you're trying to convince people of your argument. Just screaming obscenities is probably not the best direction to head. And then one thing that just was funny from that video, if I were to ask you, does gravity have anything to do with the shape of the fucking Earth? What would be your answer to that?
Yes.
Okay.
Yes. So that's fundamental to the shape of the Earth. Yes.
Fundamental to the shape of the Earth.
Yes. It's a hydrostatic equilibrium, although hydro means water, but yeah.
Well, this is kind of the thing, is that if I ever make a mistake, I'll fully admit it. And I admit ahead of time that I'm going to make tons of mistakes. But the other side says the same thing, yet they were trying to argue that fact, that the gravity has nothing to do with the shape of the Earth.
Now, can I put an asterisk besides that? When you said, does gravity have anything to do? The answer is yes, because it causes the Earth to pull into a sphere. But the second part of the answer is you don't have to believe in gravity to make very careful measurements, observational measurements, and the geometry will point to the spherical Earth, the globe Earth. Does that make sense? In other words, you could reject gravity. You could say, I don't believe in gravity, and you could still make careful measurements, and you will conclude a globe. So I wanted to clear that up. So that might be why they said no.
Okay, but I mean, most people who look into gravity come to the conclusion that it sounds like it's just a makepiece, or and from that can determine, well, if gravity doesn't exist the way they think, then there's a chance that the Earth isn't a ball. Would you say that is something? Because I'll tell you, that's my opinion. My opinion is, when I look back and I see things like dark matter, dark energy, that all these things came into play because the fact that when they look out into the galaxies and they look out into deep space, these galaxies are not acting under the rules that gravity has set. And so because of that, they've had to add other things that they can't observe, but they say must be there. Right. So to me, when I find this out, I realize, well, here's the problem with cosmology, is that they won't ever take a look at their fundamental foundation. They won't go back and look at gravity and say, did we make a mistake here? Is this really true? Because if they did, by disproving gravity, immediately the Earth can no longer be a ball. That it is the only way their so-called idea of spheres come together, and the spheres in the sky and the moon and the other planets, is because gravity takes anything larger than a few kilometers and moves it into a sphere.
Right. I would disagree. I would disagree with you on that, because if you go back, say, to the study of astronomy, say just 100 years ago. 100 years ago, there was no study of dark matter, dark energy. Theory of relativity hadn't been come up with yet, and so, but they still had very, very careful observations of the sun, moon, and stars. I mean, they still knew about galaxies, although maybe they didn't know about the motion of galaxies. Maybe their instruments weren't that sensitive 100 years ago. So you could, the dark matter, dark energy stuff, that's cutting edge research. And that's one of the things that I think really kind of muddies the water in the flat Earth debate, is that people will take something that current physicists argue over, and they'll say, well, see, they're arguing, therefore gravity doesn't exist. And my point is, you could figure out the shape of the Earth by careful observations. And the tagline for all my videos is "in your own backyard." So you could throw gravity out the window, throw dark matter out the window. Set the clock back 100, 200 years, and you could still make these observations and come to the conclusion that the Earth is a globe. I hope that makes sense.
It does. Yeah. Okay. So we will. I'm going to start by sharing my screen here, and we can get rolling. Your entire screen share. Okay. So hopefully my screen is up.
Yep.
Do you see my screen?
Yes.
All right. So we'll start with the video, and we'll go from there. Everyone, it's Jeranism, bringing you 5 facts about the Earth we weren't taught in school. These differ from any of your current beliefs. You can research each of the facts by following the links in the description below. So here we go. 5 facts about the Earth they didn't teach us in school. Number 5, the motion and blazing speed of the Earth. The actual motion, speed, and unbelievable movement of the Earth in the accepted heliocentric model of the solar system says we are spinning at 1,000 miles per hour at the equator. Now, that's only one revolution per day, but we're also zooming 66,000 miles per hour around the sun. How about the entire Milky Way, which includes the Earth and the sun, as together we are racing around the Great Attractor at 2.2 million miles per hour. That's 52,800,000 miles per day and 19,272,000,000 miles per year. Now, this Great Attractor we orbit is quite far. It's somewhere between 881 quintillion, 850 quadrillion miles, and 1 sextillion, 469 quintillion, 750 quadrillion miles away. And it's huge. Eta Carinae is 5 million times the size of the sun. Betelgeuse is 300 times larger than Eta Carinae. And VY Canis Majoris is 1 billion times bigger than the sun. The Great Attractor is 2 sextillion, 351 quintillion, 600 quadrillion miles wide. That's 2 quadrillion, 719 trillion, 949 billion times the size of the sun. And with all the distance and the crazy spiraling and turning, not to mention the yearly 585 million mile orbit around the sun, on January 1st, the stars reset. And through all those 19.2 billion miles, the North Star, Polaris, remains in the same spot. And no one has ever felt anything. Okay, so, oops.
Discover.
Thank you for that. Go ahead and tell me, or you said you have some slides or something you wanted to show, or? Oops. Well, I don't hear you.
I'm sorry. I muted myself during your presentation in case I had to belch or something. Can I do screen sharing?
Yep.
And it's only a few slides. And
Sure.
I've got a timer. I've got a timer set. All right. So it's going to be my slideshow for jeranism. So let me know. Can you see this? It says 5 facts about the Earth. It's basically a screenshot of YouTube. Can you see that?
Well, I'm probably not presenting it to everyone, so that's probably the problem. I don't see it.
Okay, so let me go back to screen.
Oh, now I do.
Oh, you did. Okay, so I'm gonna have to do it this way. I'm gonna zoom out a little bit. I don't have any transitions or whatever.
No.
So you could see this just fine. Okay.
Yep.
I just have to have a gratuitous picture of my daughter. We started potty training today, and we've had a number of accidents. But and there's my little girl kitty, Philip. So motion and speed.
I actually have a secret.
I'm sorry. What did you say?
I said, how are you going about that? I actually have a secret for potty training.
Well, set a timer. Like you have the little toy potty out there. Set a timer for like 45 minutes. Every 45 minutes, you put the kid on the potty. You read the little potty story while they're sitting on the potty, and after about 10 minutes or so, you get up. But the timer was going to go off like 2 minutes, and then baby girl made a little puddle on the floor, and it was like, oh darn, we were just about to put her on the potty. But it's day one.
Yeah, I got my son done in one day because I watched Dr. Phil, and he said to get a closet and put a bunch of balloons and a cake in there.
Okay,
he did that, and then tell your kid that all they have to do is go to the bathroom in the toilet, and they get to have this party, and you just keep filling them with juice and have them not wearing any clothes, and basically because no human wants to pee on themselves.
Okay,
they don't like the feeling of. So you just basically take them to the toilet, sit them down, say if you want that balloon and cake, then you'll go to the bathroom, and then you get up and you kind of do some stuff around the house, and 5 minutes later take them back, and sure enough, within probably an hour, he peed in the toilet, and that was the end of it.
That's
so
awesome.
I had it very easy, and I know all kids are different, but
boys are the worst. I mean, we went through torture trying to train our boys, and they're twins, so they're at the same time. But yeah,
well, that's so
good old Dr. Phil. Okay, so here's my first point, and that this animation, this wildly spiraling animation, is sped up. So. Do you have a guess? And you might have seen my debate with Jibby Jedi, but do you have a guess as to how much this animation is sped up, just off the top of your head?
Well, I'm assuming that when you see the Earth go once around the sun, that's a year.
Right. So, but the number is 300 million times. It's 300 million times sped up. And there's this neat little website you can go to, theplanetstoday.com. So what I'm going to do is I'm going to I don't know if you can still see this thing loaded up. Okay, plans today. It's gonna take a few seconds to load. But if you got this little control panel over here, and I think if you click 16 times, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. All right, 17 times. So I've now sped up this animation 10,000 times, and all we can see is the Earth is like spinning, right? I don't know if you can see that. It's a really tiny Earth spinning, but like you don't see this amazing, carnival ride, getting dizzy. So the thing is, yes, we do have these crazy spiraling motions, but they're only crazy spiraling motions if you speed them up 300 million times. So this animation is sped up 10,000 times, and we still can't see anything moving. You can't even see Mercury moving.
So we're zoomed out extremely far. So, I mean, are we moving 2.2 million miles per hour?
Well, the sun, yes, this does not represent the sun going through the Milky Way galaxy or the Milky Way galaxy. So right. Yes, but
because astronomy likes to take everything in its sector, in its frame of reference.
Sure, but that's important that you take things in their frame of reference, because if you look at our solar system, it's stable. Like the planets essentially look to be motionless. But if you get down to the human scale, smaller than a microbe at this image, then all of a sudden we have, thousands of miles an hour, hundreds of thousands of miles an hour, millions of miles an hour. And it seems really fast because we're zooming in like a human. And the equivalent would be, having like a slug walking across, the floor. Well, what if you were an amoeba on top of that slug? The amoeba is like, woohoo, there's like a big cowboy ride, that amoeba is going, zipping through space really fast, but it's a slug, So we don't say the slug is moving fast, even though the amoeba is moving fast. Does that make sense? Anyway,
I guess.
So that's my argument is that
2 million miles per hour?
I'm sorry?
I said, is any of those things moving at 2.2 million miles per hour, or the slug is moving a couple feet per?
Right, but my point is that what would be a scale that would be relative to an amoeba? Like an amoeba, well, let's say the amoeba is 1 micron, wide. Well, then the amoeba talks about microns per hour, or something like that. And so, well, how fast is the slug moving? How many microns per hour? Well, it's going to be, hundreds or thousands or whatever of microns per hour, which sounds really, really fast. If you're an amoeba and your speed, amoeba speed is microns per hour, then 100,000 microns per hour is really fast for you. Does that make sense?
It does, but we're humans, and that's what I'm dealing with is on a human scale. Obviously, if we were to take cells in our body and say, okay, well, how far is the distance between our toe to our forehead? I'm sure in cell distance, that's many, many million, quadrillion times its size. So if we were talking about that, that's another subject. But for this subject, we're talking about human scales. And, I understand relative speed. I get that. I'm assuming that if you fell asleep on a plane that was going 200 miles per hour and you woke up and it was going 600 miles per hour, I'm not completely sure you would be able to sense that change. Yeah. If you weren't a part of the acceleration. But if you woke up on that plane and we're doing 2.2 million miles per hour, I feel 100% different. Now I can't test that. You can't test that. We simply have to believe words of men who say you wouldn't feel that either.
Well, but the thing is, these things have been tested. It's part of physiology. It's part of psychology. What do humans perceive? And let me just show you this next slide, because this is actually something. It's sort of a party trick that you do when you're having like a nice little get together, not like a whole lot of rowdy people, but like a small thoughtful group of friends. What you do is you lie down face down, and you have your eyes closed, and you have a friend lift up your arms. Not that you're breaking your back, just like a stretch, a gentle stretch. Okay. And then you hold that position for 2 minutes, and it's really, really important that the person on the floor has their eyes closed. And then what you say is, okay, I'm going to lower you down now. And the person holding your arms lowers you very slowly. Say, I'm lowering you down now. And what the person lying on the floor will feel, they will feel the top half of their body pass through the floor. Okay. Because your senses are being fooled. The change of angle of your head is is detectable, but you can't really sense the rate of it. And then, of course, your stomach muscles were being stretched in that position, and they're now relaxing. And I'm telling you, if you try this, following these instructions faithfully, you will get the sensation that the top of your body is passing through the floor. And obviously it's not. Then you open your eyes and you see that, okay, I'm only a couple inches away from the floor.
So based on that, though, why wouldn't the same be true, for instance, if I'm standing facing north and I face north for 10 minutes and then I turn my body to the south? Why wouldn't the same effect happen?
Well, no, you would feel the turn. But what if you turn facing north and then it takes you 12 hours to turn facing south? You would never sense it. You would never sense. Oh, here's a question for you, Jaron.
I'm saying that if I'm facing north and then I quickly turn and face south,
yes.
Why wouldn't there be a shock to my system at that point? Because I've actually gone through quite a big change in my directional.
Only rotational. Like your bodies. For example, I'm near Philadelphia, so I'm traveling, 800 miles an hour around the center of the earth. And so it's like I'm traveling 800 miles an hour in one direction. Well, not if I turn around. Well, I'm still traveling 800 miles an hour. The only thing I've changed is my direction. So my inner ear, my sense of balance senses my change in rotation. I just changed where I'm facing, but I didn't come to a screeching halt and then go 800 miles an hour in the opposite direction. So I'm not accelerating and decelerating through, 800 miles an hour, 0, and then another 800 miles an hour in the other direction. Like that doesn't happen. I'm steadily going 800 miles an hour. The only thing that's changed is my facing my direction.
Okay, so let me try and change it then. So if the way I understand motion, and you can tell me if I'm wrong, if we're in a car, we're driving straight on the freeway, and we're going to make a left turn going 60 miles per hour, that force that I feel, which is the centrifugal force, or centripetal.
No, centrifugal is what you feel when you feel like you're being pulled to the outside of the.
So that motion that we feel that's going towards the outside, that's simply your momentum was going straight in a straight line, right? And as you start to turn, it's the momentum that you would feel because you were going straight. That's why you're pushed against the door of the car, the passenger side door, correct?
Yeah, because your body wants to go on a straight path, but the car is forcing you to go on a curve. Therefore, you feel pressed up against the wall. And it's a very real force that you feel because you're in a rotational frame of reference. However, a third-party observer, it's a fictitious force for that third-party observer. If you open the car door, you will travel in a straight line,
But if I turn around and face the other way in the car, so now let's say that the passenger seat is on a swivel, and I turn and face the back of the car, well, now the left side of my body will be forced against the door, whereas before it was the right side.
Yes.
So I would clearly know the difference. If I was driving in a car on a freeway going straight, and I felt the car turn to the left, I would go out to the right, my right arm and everything would be going out. And if I turned around and we did it again, it would be my left arm going out. I would be able to tell the difference if my eyes were closed.
Yes,
right?
Absolutely. And so this gets to the question of centrifugal force on say the rotating Earth or the orbiting Earth, or, and if you run the numbers, it's a very, very small amount. It's 1/3%. If you run the numbers, it's 1/3% centrifugal force. And that's not detectable by human beings. It's too light to be detected.
Okay.
So, I mean, it's a valid argument. And the thing is, the flat Earth debate is full of arguments that make really good sense, which is why I really get annoyed when people call people stupid all the time, because these are good concepts. But run the numbers. Take a standard centrifugal force, formula, and then just put in the numbers.
And I have a lot of people ask me, why do you talk to Charles? Why are you going to have a hangout with Charles? And let me just explain why. Because when you say things like that, it gives me hope that you would see that. Does it bother you, or does it kind of seem funny to you that so many people were taught the stupidity of flat Earth? Because here's my thing, and these are all things that led me to my belief. A lot of people think I popped out of a cave and just said Earth's flat and made videos. And that's not at all. I went through the same schooling everybody did. I didn't spend a lot of time in college, but thank goodness. And I feel like at this point, when I look at everything, there is a story that unfolds that certainly does not lead to well, heliocentricity is the truth, and they knew this, and so they taught. No, why would you teach flat Earth is stupid? Why would you call it an ancient desert wandering belief when it has a lot of good arguments? The better method there would be to explain to school children why we know that the Earth is not flat, and that's not something that's taught in schools. It's glossed over. They don't ever mention anything about any kind of an ice wall or containing water. They want people to think water falling over the edge. They want people to think people falling off the edge of the Earth. They want to think the Earth in space. So these things, along with the Coriolis force and water going down the opposite way in hemispheres, and all these things, when you realize that they are almost lies told to kind of get us to believe what they wanted us to believe, doesn't that alarm you? Doesn't that seem like a problem?
Well, there's several layers to this question, because, and you know, Jaron, that I believe, and I don't think it's a belief because I've measured it myself, that the Earth is in fact a globe. And so at one level you have reality versus a belief structure. And so I'm very sorry if when you were in school that they made a big deal about how flat earthers were stupid. I mean, I never got that when I was in school. I was taught the Earth was a globe and that people used to believe it was flat. Yes. But I wasn't, they didn't layer on the salad dressing of, oh, flat earthers are stupid. Like I didn't get that part.
You didn't think you ever saw that throughout your life? It wasn't like a pushed narrative?
Well, if references come up, I mean, of course, Obama's really been pushing it because, I mean, he's got, some speechwriters that just repeat the same phrases over and over again.
Right.
So that's, that's kind of unfortunate that it's now, synonymous as far as Obama's concerned, synonymous with stupidity.
Mm-hmm.
But the thing is, there are several things that were considered to be truthful and then were discovered not to be truthful. For example, heavier than air flight. We know that the Montgolfier brothers, set up a hot air balloon. This is like in the 1700s. And so it's like lighter than air flight, where you're using buoyancy. That was known for hundreds and hundreds of years, but people were like, well, flying, in a craft that's heavier than air that does not use buoyancy, that is impossible. And a lot of scientific people thought it was impossible. And then the Wright brothers came along and proved them wrong. And so it's like, so the reality is heavier than air flight is possible, but people used to believe that it was impossible. So that's where
everything science came up with, say 300 years ago, has already been shown pretty much to be wrong, right? I mean, science is a progression towards the truth. There's not a lot of things that they haven't corrected or fixed or understood better.
But it's an iterative process, and sometimes science gets something like super wrong. Like there's certain medical procedures which are just ghastly. If you were to describe them to somebody, they're like, no, that's mainstream science. And it's like, yeah, it was medical practice, by a bunch of men. I mean, don't get me started on childbirth. I mean, they used to torture women, in the name of medicine.
They kept bloodletting, even.
Oh my goodness. But over the long cycle. Over the short cycle, you may have some really serious errors, but over the long cycle, hopefully these errors get corrected. And part of the scientific process, and I'm not going to say capital S scientific, lowercase s, is you have an experiment, you get some results, but then you give your experiment to somebody else. You say, hey, here's what I did. I'm just describing my apparatus. Here's how I did the experiment. See if you can get the same results. And then people tweak the apparatus. They're like, what if you substitute in steel for wood? What if you try a torsion rod made of quartz fiber? And then they get better and better results. And that happens over hundreds of years by many, many, many people trying these things out and getting their hands dirty. And that's really where the body of knowledge comes in. And so the numbers get better, like what was the estimate to the sun? 1 million miles. Okay. And then what was it? 50 million miles, and then it was 100 million miles, and then it was 90 million. Yeah. Just so it's like, the estimates, they kind of vary on, but they're going to get closer and closer and closer to like an asymptote, closer to the actual value, just because as technology improves. So Jaron, we've been on this one 15 minutes. We kind of sort of informally said maybe 20 minutes per topic, just so that our audience doesn't get bored to tears. But we're at 18 minutes. Right now. No, that's it.
So that was your end of number one?
Yep.
Oh, or number five. Okay. And yeah, just to kind of finish off my piece.
And it says that I'm still presenting, so you're going to have to take the controls back.
Yes. So I know that for me, when you hear about those speeds and the motion of the Earth, my simple answer would be I have no problem believing that if I'm shown some sort of proof. And there is no proof. There's pretty programs like you just showed. You can go to lots of websites that have the motions spelled right out there for you, but they're simply mathematical equations plugged into a CGI video. And if you plug that in, then everything works. And I still have a problem with that, being you just mentioned that the sun was originally 1 million miles and Copernicus said it was 3. Well, I'm not really sure that can be shown to be true, because if you were to plug in 3 million miles instead, everything else gets thrown to crap. And we're told Copernicus is this mathematical genius. He would have known that his 3 million mile sun was wrong, but he didn't know. And I think that, and again, publishing something on your deathbed, something I simply don't believe in. Again, I'll admit full on that that's my belief. I'm not saying because I believe something, it has to be true. I'm just saying, I think I know human beings. They don't publish books the day that they die. It just doesn't happen. It seems to me to be something that was written by people after him who wanted to not put their name on it, put his name on it. And who could argue with that, because that's all we don't have much information about him at all.
Can I say one last piece about, how you said like that computer program that's showing the solar system? The thing is, all those values, they are all confirmable by you with binoculars. For example, Venus is really high in the sky.
If that's true, why
the highest point in the sky? And you could measure the angles. Like an amateur, you're not paid for by anybody. You could measure the angle that Venus makes with the horizon. You could time its motion, and then you could take a look at that computer software, and it's all going to match. Like, you're not going to find any contradiction. Which means that either it's a really sophisticated computer program that's faking reality, or that it is mimicking reality. Like there's, so I don't know.
Well, so why, if it's so easy for me to do it, why would Copernicus have been wrong?
Well,
why would these guys?
What was the year? Was it 400, 500 years ago?
Yeah.
The telescope had not been invented. The theory of gravity had not been invented.
Let's go ahead to Galileo, 1650 or whatever. So he had the telescope. He was able to see the moons of Jupiter. I believe shortly after him, they saw the rings of Saturn, which doesn't make a lot of sense, because even my 8-inch Dobsonian barely showed the rings of Saturn, yet we're told to believe that people in 1600 were able to see them. But explain to me then, when you make it seem so obvious that it's so easy to tell with you said a pair of binoculars, which is probably equal to what Galileo had at his best, would have been about the, would you say it would be about binocular strength?
I don't know. I mean, possibly, but
but you make it sound like it's so easy for us to tell. We can just go out and measure these angles. Why weren't they able to?
Well, for starters, our starting point is on the shoulders of giants who are standing on the shoulders of giants. I mean, we are so far ahead. So, for example, we have a website that shows the positions of the planets. And actually, that website, I believe it's a horoscope website, because you might have noticed all of the 12 signs of the zodiac, because they're facing the different directions. But they didn't have that software back then. I mean, everything was done on paper. So, he's going by his measurements as an observer on Earth, looking up in the sky and seeing this bright dot and then giving it a name, Venus, Jupiter, whatever. But today, in hindsight, we know exactly the orbits of these things, exactly where they are, the proportional distances, proportional speeds. So it's like, that's our starting point, is all this knowledge. And so we can't just, take a look at him and say, well, how come he didn't figure it out? He figured out a lot, right? We should give him credit for that. But he didn't figure out everything. It's kind of like the 3 million mile estimate to the sun. It's like, how come he didn't come up with 93 million? It's like, well, he did the best he could, and that's another part of science, is that, you try to iterate and try to get, incrementally better, but you don't criticize the people who came before you for not getting it perfect.
I guess it's just if they supposedly knew the size of the Earth when Copernicus was around, right? I mean, that was pretty much a known thing.
Right.
Okay. They knew the equator distance. So once you know that the size of the Earth, and then you put the sun to be only 3 million miles away, then your orbit becomes exponentially smaller than 584 million miles.
Sure.
And then as a result, don't all the other planets have to be reduced in size? Doesn't everything have to be scaled down?
The orbits scale down, sure, sure. But when you think about our solar system, and I don't know if you've seen any of these visualizations where they zoom out and zoom out and zoom out. It's like 10x, 10x, 10x.
Right.
It's a lot of empty space. I mean, it's a ridiculous amount of empty space. And so if you scale the Earth-Sun orbit to be 3 million miles, it just simply scales down the size of the orbits of the solar system. So instead of the Earth going 66,000 miles an hour, the Earth is now doing 20,000 miles or 2,000 miles an hour. I mean, I'm just making these numbers up. You just scale down the size of it, but you still end up with a whole lot of empty space. Because 3 million miles is still a huge distance away. But then of course the size of the sun would be reduced so that it appears to be a half degree or 30 arc minutes. But it doesn't kill the model. It doesn't throw the model in the trash can. It just scales the model, which is why one of the fascinating things. I'm sorry.
It could be anything. So what based on what you just said,
sure,
we could double the distance to the sun, double its size, double all the orbit sizes, and how would somebody know that you're wrong?
So that's a fascinating topic, and the figuring out the distance to the sun involved figuring out the distance to Venus. And I think you've probably heard the story where they had a guy down in, I don't know, the South Pacific, some island in the South Pacific. They knew that Venus was going to transit the sun. It happens only twice every 100 years. And so I think it was Halley, if I'm not mistaken. It was some key astronomer, and I don't know my astronomy history, but basically he knew this was going to happen, and he wrote down instructions because he would be dead when this thing happened. So he wrote down careful instructions. He said, I want, one guy to be on the other side of the Earth, another guy to be on the other side of the Earth, and I want them both to observe the transit of Venus of the sun and take careful measurements. And I don't know much more of the story than that. And because they're triangulating, knowing the size of the Earth, they could triangulate the transit of Venus, coming up with very careful observations. And then it took them like a year just to get back to report in, by ship travel. But like that's part of the story.
Can you triangulate with a curved baseline?
Yes, because if you know the dimensions that you're talking about, and for example, latitude and longitude were invented, I don't know, like 500 years ago or more. And so if you know very accurately the two positions on the globe, then you know the angles. This. I mean, spherical geometry is 1,000 years old. So yeah, you can absolutely do baselines with a curve, on a globe.
Okay, so what I'm kind of getting at there is that it's a different number if you were to take your two positions as level and flat, and then if you were to take them with the curvature of Earth involved.
Yes, but here's where the problem comes in. The observations don't make any sense if it's flat. I know we've had this conversation before about Eratosthenes and his sticks,
which
and
is
shadows.
one of the numbers which we're going to get to. So
yeah, but the thing is, it only makes sense with two observers. It doesn't make sense with three. So like the transit of Venus of the sun simply makes no sense unless the sun is millions of miles away. That Venus is millions of miles away.
Based on what you just said, if we scaled everything down, then it would make sense. You just said that it's equal. So meaning that when they watched Venus cross the sun, they're taking the angular size of Venus and they're measuring the angular size of the sun, and then it's passing in front of it. So yeah, I see what you're saying, but I kind of don't when you can scale it down. So
when I said scale it down, I meant scale down the solar system to be still the solar system, still a heliocentric solar system. I did not mean scale it down so that you are now looking at just lights in the sky above a flat Earth, because then the measurements, the numbers just go, all of them just go right out the window. At first blush, it kind of makes sense. 32-mile wide sun appears to be 30 arc minutes. At 3,000 miles in elevation, at first glance, the numbers might kind of work, but the numbers, the observations just don't make sense.
Right, and it's something that's going to take time. Just like you said, it took them hundreds of years to correct their mistakes, and they had obviously big ones going from 3 million to 93 million. A lot of errors in there, a lot of room for correction, and the flat Earth is the exact same. that to think that 2,000 people on YouTube are going to be able to present a model that matches and meets our observations perfectly is crazy. It's not going to happen. It's going to take time. It's going to take a lot of resources. It's going to take minds from all over the earth. It's going to take a lot of work to get it down. And so, I mean, when people come and say, well, how far is the sun? And it's 32 miles and 3,000. I don't believe it's 3,000 miles away, but it's going to take time for us to, be able to present something that is close to being as accurate as the globe model is. The globe model.
Did you just say as accurate as the globe model is?
Well, because I don't expect it to be anything but that, because they've had 500 years to craft mathematical. Go ahead.
Yeah, but it sounds like you're calling the globe model accurate, because I mean that's my argument, is that the globe model is accurate, extremely accurate. But anyway,
and you know what?
So we're at the 30-minute mark, by the way.
Is it true? That's the problem. Is that it? Just because something is accurately portraying what we see with our eyes, it doesn't mean that that's reality. And so that's where you step in and say, okay, let me see the proof for these things. And when you're not shown proof, then you try and take some steps back and say, okay, were we correct from the beginning? All right, let's go to number 2. Let's see here. Share. Okay, number 2. Gotta get through this ad first. Who put these ads on here? Crazy.
So just Jaron, it does say that I am presenting to everyone. So just want to make sure that.
Thank you for telling me that. I have my name down. Present to everyone. Okay, now you should see my screen.
Yes, the sphere goes way back. Yes.
The sphere goes way back. Did people 500 years ago, 1,000 years ago, 2,000 or 3,000 years ago believe that the earth was flat? In school, we are taught that Columbus discovered America and proved the globe. But now they call that a myth. They now say that no educated person after 500 BC believed the earth was anything but a sphere. They even tell us about Aristophanes and that he measured the circumference and came within 2% of our current 24,901 mile equator. That was back in 275 BC. It is a cute little story, but clearly one of dreams and not reality. First off, no books of Aristophanes have ever been found or survived antiquity, so any belief in such an experiment would be hearsay at best. And in order for the test to work, one would need to know that the sun rays are coming in as parallel rays. And Aristophanes in 275 BC would need to know that, even though this is what he would see. And even if he did know that the sun was extremely far away, then he would also have to believe that this infinite sun went all the way around the earth in 24 hours. Anyway, it's a nice little story, but it's untrue. In fact, flat earth must have been around, considering we have maps for ages, but the oldest globe we have is 1492. Yes, they knew the earth was a ball back in 275 BC, and just waited about 1,800 years to ever try and make a model of the earth on a sphere. Okay, you're up.
All right, so let me just present a little bit. I'm going to say application window.
I believe you're on.
I'm just going to present my entire screen. Is that okay? Sorry about that whole infinite thing that looks so silly. Okay. So the sphere goes way back. So I would argue that the fact that there are no surviving globes that are older than 500 some years it's an anecdote, and it's like, oh, how come we don't have any globes back or earlier than that? But apparently the manufacture of globes didn't even take off, like as a worldwide phenomenon, didn't take off until say the 1500s. And so. And I'm just throwing these 2 book covers up here. And again, and my caption is not proof, but study the history, because it would be interesting to learn, who made that globe that still exists. I think it was, I forget the guy's name. But it would be interesting to study what we do know about people who made globes, or about the history of the globe, even if you don't agree with it. If I'm not saying it's proving anything. I'm just saying it would be nice to study what they knew. And so from the blurb about the book called Globes, it's talking about there being descriptions from either Plato or Aristotle actually described how to construct the globe. And then one of these guys actually wrote down the latitudes and longitudes of all these cities across the world, and they were using data that they had gotten from other people, because like they didn't visit 4,000 cities, but they had an almanac of cities visited by other people. And it's interesting that they say the oldest surviving globes are actually celestial spheres, celestial globes, dating back before 150 AD. So again, this isn't evidence of anything, but one thing that I think a lot of people might not understand, because the flat Earth really just sort of stretches out the southern hemisphere, is the concept of longitude. And longitude really is about time. So it's 365 degrees over 24 hours. And the measure of longitude was a huge problem for sailors, because they didn't have any accurate ways of keeping time. And so this book is about John Harrison and his invention of the chronograph, so that they could measure time at sea. And if they could measure time at sea, they could then accurately estimate their position. And the thing about longitude, though, is you take a look at a globe and you take a look at the map of Australia and how it's all, looking like it's stretched out. That's because of the longitude. I mean, it spans so many degrees of longitude. And so on the equidistant azimuthal projection, it's also stretched out. But so you can't just shrink it back down into the Australia shape that we know and love, because then you're messing up the longitude. And the last thing is, I just want to talk about this globe maker, Bellerby and company. These guys make globes that they sell for tens of thousands of dollars. And so there's a number of very interesting pictures of them, hand painting these things. I mean, they start off with paper strips, and then they glue them on, then they hand paint them, and they varnish them. And it's a fascinating study. But I included this image because there's Antarctica over there on the left, and it's like maybe Antarctica is in fact a continent. It's not just the stretched out edge of the flat Earth, because these guys aren't just making up the shape of Antarctica. They're not making up the shape of Australia. And that is the presentation.
Making it up, but it's what they were taught to do, right?
Yeah, but the thing is, you're discounting surveyors and explorers who, say a seafarer, he has a sextant so he can measure the heights of stars and the sun and the moon. So he knows the heights of things in the sky, and he also has a chronograph, so he knows his longitude. So then he knows his latitude and longitude, and so he visits various ports of call, and so then you can actually make maps using a ship captain and accurate data. And then on land, obviously, the same is true with surveyors and their theodolites.
Mm-hmm. One weird thing that, I don't know how many people know this, but if you look into the history of Cook, Wilkes, Mercator, Magellan, these guys who did these expeditions, that when they got back, they turned their logs over to the Queen, and it was often 3 to 4 years until those were released to the public. So that's peculiar, because it sounds like somebody wanted to possibly make some corrections or to adjust some of the numbers. Certainly seems like it would be something that they would be happy to get out to everybody, but sounds like they were trying to change some things. I mean, to me, it's just showing a globe and saying, "Oh, that those people are not making up Antarctica." No, but I mean, we can look at proof. Right. And Cook said he could never get to the southern continent,
right? Because of the ice. Because the ice. There are lots and lots of ice. I was reading about how Antarctica, the first people to discover Antarctica, and it's credited to Cook, but it says that he's the one that found evidence of Antarctica. And then there was another guy who first laid sight on Antarctica, and it wasn't a year later until some third ship captain was actually able to set foot on Antarctica. So, I mean, people don't understand the hazardous nature of sailing close to the Antarctic Circle. But here's a question for you. Are you familiar with and I'm not going to pronounce it right, it's French, Vendée Globe race? It's VENDEE, yep. Globe. So I think it's going on right now. At least it was going on a week and a half ago. And these guys are basically, they start off in, I don't know, the Mediterranean. I don't know if it's, the Europe somewhere. They sail down between South America and Africa, and then they turn and they go east. And the idea is for them to essentially circumnavigate the globe by the southern route. In other words, they're not going through the Panama Canal or anything like that. They're not going through the Suez Canal. In other words, it's a southern hemisphere circumnavigation. And so you have competing what do you say, variables. In other words, if you travel further north, you're going to have warmer climate. If you travel further south, you have a shorter distance. And so that's what makes it an interesting race. Correct. Is that these guys are going to be skirting icebergs. They're going to be getting as far south as they can to make the journey as short as possible. But then it's a much more hazardous journey, even though they're reducing their mileage. So I don't know when the race ends.
Could be around January 5th or something, I think.
Okay. But then if you take a look at their logs, and the thing is, every single one of these ships has tracking devices. And so there's an automated display where you can actually see there's one ship that, it's like, wait a minute, how come that ship's going backwards? Well, it turns out that ship dropped out of the race.
Yeah, I know. It's fun to look at
that. And then, yes, one of the ship captains is named, what is it? The Builder, not the Bilderbergers, but the, what's that big, it's one of these big names, and they're controlling the world. The Rothschilds. One of the ship captains is named Rothschild.
Right.
But it's a really interesting. It's an interesting race. But if you look at the logs, and you can animate it, like 100 times sped up, so you see the little ships going along. You can actually see how fast they're going, and they're going about as fast as a sailboat would go, in water. But the thing is, you take that same exact display and you stretch it out onto a flat Earth map, and all of a sudden they're going, not exactly Mach 2, but they'd be going, like 100 knots in a sailboat, which is not possible. Anyway, it's not proof.
Yeah, I don't know what you mean by that. 100 knots. They're not.
That's 100 nautical miles per hour.
I'm saying nobody's going that fast.
Right, nobody's going that. But if you put their trajectory, if you put their path onto a flat Earth map, that is got the North Pole in the center, then all of a sudden they're going the long way around. They're going around the outer circumference of the flat Earth map, and then they have to be going a lot faster than they actually are, because the further south you go on the flat Earth map, and again, pick your map, you increase your distance, whereas the further south you go on a globe, you decrease your distance. In other words, you decrease the circumference on the globe.
Okay, so, I'm going to be doing a video about that, both the Vendée and I don't know if you've seen the Volvo one.
No.
There's another race that's coming up, the Volvo one, but that one there, they admit, they like to talk nautical miles because people don't really convert those very well, but the Volvo is 51,000 miles.
Okay.
And their path is not something that looks to be at all that much. Now, how much is the Vendée Globe? Isn't it about 26?
I don't know off the top of my head. I really don't. It's however long it is from Europe to the southern tip of Africa, and then they have to go, I think, south of Australia and south of New Zealand, if I'm not mistaken, and then south of South America, and then turn north and then go back to Europe. I don't know where the starting point is. Maybe France. But it's a fascinating, thing to look at, especially now that all these ships all have tracking, all these tracking devices.
One of the interesting things, they're not even allowed to talk to people on the ship, besides their main captain or their main manager or whatever. But those people aren't even allowed to give them weather conditions. It's all part of the race. You got to play the weather. You can't know ahead of time. You're not allowed to use GPS equipment to predict the weather. You can only know your location and where you're headed.
Yeah, I don't know the specifics. I do know I was watching the animation, and there did seem to be one point in time where all the boats, they all angled south. Like they were kind of sort of going in an easterly direction, and then all of a sudden there's a little right angle where all the boats headed south. And I'm wondering if they got an alert, a weather alert that was maybe some typhoon or something, and they were all trying to steer clear of.
Because they do change the route throughout the race if there's some sort of weather conditions they don't want to be going into.
Okay. Can you pause for? I mean, you could fill the time with 30 seconds. I need to give my son something. So 30
Sure.
seconds. I'll be back.
No problem. So anyway, yeah, I want to do a video about that because one interesting thing is also that they do go east around the Earth, and if there's the reason for that is because the wind goes east. So my question again would be, if the Earth is spinning to the east, then wouldn't the wind, if anything, go west? Yet the wind goes east, and that's the reason you can't even have a sailboat competition really if it was going the other way. It has to go east because they have to use the wind. Granted, I think in sailing you can always go forward based on the way you move your sails. You don't ever have to go backwards, but it would just take twice as long. And I believe that one race is about 2 months or 2.5 months, really.
I'm back.
Thank you for what would be the reason for? Okay, so the Earth spins to the east, and all the wind goes to the east.
That's above my pay grade. I'm sure meteorologists can explain that in terms of an Earth Sun dynamic. You know, but I don't know.
Okay. And do you have anything else on that one?
No, that's it.
Okay. Well,
and I'm still presenting. So.
Yeah, sorry. 1,800 years of no globes seems questionable to me. If you were, I mean, they say these guys knew the longitude and latitude way back when, which means they knew where the poles were. They knew exactly where the North Pole was and the South Pole was, which means they also knew how small of a section of land they occupied, which means they should have known way ahead of time about their possibility of other land on the other side of a globe. But the whole idea of Columbus sailing was to get to the Indies the other way, right?
Yeah.
That's the whole thing. So it's just when you look at the whole history of it, it doesn't make sense. It doesn't make sense that these guys knew the circumference of the Earth. They knew it was 24,000 miles around, or let's say they thought it was 26 or 22. It doesn't matter. They knew how small of a section they occupied, yet nobody wrote about the possibility of there being other land on the complete other side of the globe.
When I was looking into this, especially the whole thing about Columbus trying to find India, it seems that there was a systemic error in their estimates of latitude and longitude, and like maybe their lines of longitude were not measured correctly. I mean, for example, we now measure longitude from the Greenwich meridian in the United Kingdom, but it wasn't always so. The longitude used to be measured from some other city, but I have not studied this, so I'm really, this is a very partial understanding. But what I gather is that Columbus, they kind of thought the world was smaller. I mean, like they kind of knew the circumference, but maybe they didn't know the circumference at the same time. Like
you're just explaining exactly what I'm saying.
Yeah.
Don't you see that there's errors along?
Sure,
that's
absolutely.
The Aristophanes story is a story. It's told after the fact because they know now. Let's just say they know now what the equator size is or what the Earth's circumference is. So once they know that, then they can look at all their little things and they realize, hey, by looking at these shadows, we can say this shadow equals this amount of difference versus the shadow that has the sun above it. And so they crafted a story and applied it to somebody whose books don't even exist. We can't go back and see the method that he used. How did he get 500 miles away? How did he communicate with the person 500 miles away?
Yeah, well, it was a year. It was year over year. It was the what was it? The summer solstice, the sun being highest in the sky, and then it went down into that well at Syene. So it wasn't it wasn't communication with two people. It was basically he knew the light went down the well at Syene on the summer solstice. So all he had to do was measure at the summer solstice how high the angle of the sun. So it was basically himself. But
if you know everything that we know today.
No, and it could be mythology. Okay, so throw the guy under the bus. And by the way, Jaron, this really bugs me. Aristophanes was a poet. Eratosthenes was the librarian at Alexandria, who did this. So it's with an E, Eratosthenes, Eratosthenes.
Yes.
Aristophanes with a PH. Aristophanes was a poet. Okay, and actually, there is a book of his that does survive, but it's just a pronunciation thing. Anyway,
Eratosthenes. You happy?
Eratosthenes. Yes,
There you go.
Eratosthenes with Eratos. Eratosthenes.
Yes, I'm not using a PH.
Okay, that's fine. But anyway, we're 49 minutes in.
Okay, let's go to the number
three.
3. And I think I'm sharing. I don't know. Let me try this again. And I think I'm presenting.
Yeah.
Beautiful. Okay. Number 3, the old Coriolis wives' tale. The Coriolis effect was definitely overblown to epic proportions when taught to our growing minds in grade school. Despite what we were taught, and despite what swindlers at the equator might show you, water in toilets or tubs does not go down the opposite way in the northern and southern hemisphere. In fact, this force would be extremely small and hard to see, especially with other forces which always exist. You would first need to distinguish the direction of deviation caused by the Coriolis force operating on its own, and the direction of rotation when other forces are present. Both directions of rotation are evident in both hemispheres, depending upon whether the flow is around a high-pressure area, pointing radially outward, or a low-pressure gradient pointing radially inward. And please remember, there is no preferred coordinate system when talking about the Earth. Once you adopt a coordinate system, one gets a bunch of forces with it. And when you shift coordinate systems, some forces vanish and others appear. In an inertial coordinate system, there is no Coriolis force. In a rotating one, there is. Basically, it is a lot of nonsense, and even referred to as a fictitious force. On the site avan.com, the following is said about pseudo-forces. Today, we will ask a few questions such as, what is a pseudo-force? What is a fictitious force? Are pseudo-forces real? Is gravity a pseudo-force? Alas, we will not answer these questions. As far as I can tell, nobody knows and nobody cares. Or at least nobody should care. If these questions have answers at all, each answer is a matter of opinion, and opinion is divided. There are no consensus. When I asked several hundred physics teachers via the Phys 1 mailing list, nobody seemed to have any firm opinions. I don't have a firm opinion either. There is no experiment you can do that will tell you the answers to these questions. For example, as far as I can tell, gravity can be classified as a pseudo-force, or not. It's 6 1/2 dozen of the other. You can choose to do it either way, and the choice has no observable consequences. The fact that there is no easy answer suggests that we are asking the wrong questions, and that we should ask more physically meaningful questions instead. Number 2. Okay, so you can refute that.
All right, now that's what I'm going to refute. I'm just going to, say a few words about that. So I am presenting, I guess. Let me see my screen, your entire screen, share, and let me go back to Keynote. Okay, so you're absolutely right that they did tell us an old wives' tale in school. But the thing is, I've been hanging out with school teachers for 21 years, and these guys, it's a mixed bag. And the thing, sometimes elementary school teachers, I guarantee you do not understand the principles involved. So they'll say toilets turn the other way, toilets swirl the other way in Australia. Like that, I heard that growing up. I don't think it was ever part of a curriculum. Maybe they might have mentioned it, talking about the globe. But I think you are exactly right that this has been overblown. So in that we are in agreement, and that there is.
Do you think it would be found in any textbooks?
It's possible. Textbook writers are notoriously sloppy. But the bottom line is, in toilets and in, say, sinks, toilets and sinks, there's no Coriolis force. At least the Coriolis force is so much smaller than just the movement of the water. I mean, like if you just pour the water in the sink going one way, and I think you mentioned the con artist at the equator. Apparently there's tour guides at the equator, and they'll be standing on the line, and they'll have a basin, and they'll fill it with water, and they'll literally walk across the equator to the other line, and they'll, of course they're going to fill the basin up. I mean, it's a magic trick, essentially, right, what they're doing there, and they're con artists. But What I did recently discover, because I didn't think it was possible in a basin, but I guess it was the guys Veritasum and Smarter Every Day. They did one where they took it was something about the size of a kiddie pool. It was like 10 feet in diameter,
Right.
And they had a drain in the middle, and they did an ingenious thing because they couldn't reach in and pull the plug. They had a hose come out with a valve. So when it was, they let the water sit for 24 hours, maybe even 48 hours until that water was not moving. And then they just opened the valve, and then they dripped some food coloring into the water to see, if they could start seeing the swirl. And, one guy I think was in Australia, the other guy was in North America, and they did go the other way. Now, I'm going to call that an anecdote. I'm not convinced that the Coriolis force works at that small a level. I am convinced that it does work with hurricanes. And you made a very good point about high pressure versus low pressure systems. It's a very, very good point. If you have a high pressure system, the winds are going to be moving away from the center. They're still going to be diverting. I don't know if it's to the left or to the right. I forget which. But
high pressure.
So but the low pressure system, the winds are rushing towards the center. They're also deflected via the Coriolis. So yeah, that's going to swirl. What is it? Hurricanes in the northern hemisphere go counterclockwise.
But that's not an always thing.
To my knowledge, I don't know of any exception to hurricanes turning the wrong direction in the northern hemisphere, and then I think they call them typhoons in the southern hemisphere. I don't know of any exceptions to that on the hurricane level.
I will get you some example, but that's more of a weather phenomenon, right? And I guess when you think of the flat Earth idea or the flat Earth map. When the sun and moon are doing their clockwise orbit or rotation above, whatever you want to call it, anything on the inside of that to the north would be deflected to the right, or which would cause a clockwise swirl, and anything to the left of that is going to cause a counterclockwise swirl.
Yeah, no. So if we're moving towards the center, so if we're in a hurricane in the northern hemisphere, and you have two lines and they're both going towards each other, they're both going to be deflected to their right.
To the
which
right.
means to the line is going to be deflected to its right. Because it's traveling faster than a higher latitude. So it's going to be deflected to its right.
Which would be clockwise.
Which would end up being counterclockwise. So if you have a line that's going south, and then you have a line that's going north, and they're facing each other, they're pointing towards each other, and the line going south diverts to its right, and the line going north diverts to its right. Well, where do they hit each other? They're gonna produce a counterclockwise spin. If that makes sense.
Not exactly. I'm kind of confused. What do you mean a line from the north?
So just take two arrows.
Okay.
So we're in the middle of North America. We have one arrow pointing south, one arrow pointing north.
Okay.
And I don't know if I'm mirror imaged on my little screen here. So this one is going to divert to this way, and this one's going to divert to this way. So now we have two lines going this way, which means it's going to be twirling around this way.
So that would be to the left.
Well, no, it's diverted. The lines are diverted to their right.
Okay, you are inverted.
Which is producing a spin. And do you see me raising my right hand or my left hand?
That's your right hand.
This is my right hand. Yes. So this is these guys are going to their right. They're being deflected to their right, which is going to produce a counterclockwise spin.
Okay. Yeah.
As you're looking down at the ground.
Okay.
Now,
it would be anything going in clockwise rotation, and then that would be deferring to your right, which would keep it clockwise, but anything to the left would be counterclockwise.
Yeah, clockwise would be if you were diverting to your left, say if it were a high pressure system diverting to your right but moving away from the center. I guess that would be more accurate. But the thing is, high pressure systems don't form hurricanes. They're just high pressure systems. But they'll produce wind, but they won't produce like a hurricane.
Yeah, I guess my only problem with this whole thing is I'm not somebody who says the Coriolis force doesn't exist. I do think it exists. I just think it's for a different reason than what they tell us, and the one that they taught us in school being oh, it affects the water in the tubs or in the sinks,
Right.
is a wives' tale, is a
Yes.
lie, and
Yes.
adds to what I talked to you earlier about. That
Right.
doesn't it seem funny that when you tell the truth, you don't need to lie. You really don't. You
You don't need to dress it up.
Right. And yet the heliocentric belief, the heliocentric understanding always had to be dressed up. They had to tell a story about Eratosthenes.
Eratosthenes.
Yes. They had to tell a story about the Coriolis force. They had to, all these things have to be talked about to dress up what they're saying is the truth. And that seems shocking to me. And then when you see them dressing up the idea of a flat earth, is not dressing it up, dressing it down, calling it stupidity, calling it ancient desert wandering beliefs, that then you realize when you look into this, that there's a lot going for the flat earth idea. There's a lot that makes more sense, seasons, things that we'll get into here in a minute. But the fact that the globe had to be forced down children's throats at the age of 6 and constantly in your face and constantly talked about, that it just seems awful funny that they're trying to get you to believe something. It's not like, oh, these people will easily figure out eventually that the earth is round. They needed to force it to you that the earth was round. It wasn't allowed to let you come to your own conclusion there.
Yeah. And I would just argue back that it's a matter of reality versus non-reality. Like, for example, how many states, were you taught when you were a child? Did they teach you there were 50 states? Did they shove that down your throat? And you're like, yes, they shoved that there were 50 states down our throat, and they pointed to the flag, and there's 50 stars in the flag, and blah, 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 blah. Well,
right.
But that's actually the truth. You could say they shoved it down your throats. And you could also argue, like, well, there's the District of Columbia. Isn't that the 51st state? And there's Puerto Rico, and then there's the Virgin Islands, and then there's Guam.
What you're talking about, the equivalent would be that we grow up, and like the whole time they said we had 50 states, and as you grow up, they're telling you 30 state countries are stupid. That they're
Right.
ridiculous. It's an ancient desert one, and then as you grow up, you look at the 30 state idea, and you're like, wait a second, how come this has so much validity? Why did they tell me it was so stupid? So when you just say that they didn't force 50 states down our throat, I'm only saying that. I wouldn't say that they forced the globe down our throat if I got to this age, looked at the evidence that led them to believe that, and said, oh, this all adds up. Oh, this all makes sense. The opposite is happening. I'm getting to this age and saying, hey, I don't understand the whole globe thing. Let me go look at it. And when you look at the progression of them discovering this, it's not littered with evidence and research and facts. It's littered with words and mathematics and conjecture and ideas and philosophical ideas. So that's the problem.
It's got all of those. You're correct. It's got all of those, but it also has a mountain of evidence. Kind of like you fly on an airplane, and there aren't still people saying, well, airplanes can't fly because it's heavier than air. And if they still said airplanes can't fly, I mean, you're going to say that person is deluded, because the people who are actually flying are disproving the fact that, the belief that their airplanes can't fly. And then so I'd argue back, with the whole flat earth thing, is that the globe has been measured, described, analyzed, and there's like so many things that are just, it's like an interlocking 3-dimensional puzzle that doesn't contradict itself. And yet, yes, you could go back in history and talk about this person said this and that person said that and this person said this was stupid, but that's not real physical evidence. The physical evidence is, can we measure curvature? Yes. The physical evidence is, can we observe the curvature from a Dwayne Kellum's, helium balloon? Yes, we can. Have we sent people into space? I would argue, yes, we have, landing on the moon, et cetera, sending probes to other planets. And it's like, but if you disbelieve in all of that, you just say, well, no, NASA's fake and everything NASA does is fake. Well, then, okay, well, maybe it's still a flat earth. There's this great quote. It's like, don't let the people who say it's impossible, interrupt the people who are actually getting it done. I'm kind of butchering that quote, but
okay.
All right. Number 2.
Everything for that one?
Yeah.
Okay. Let's go to number 2. Hope I get a share.
Oh yeah, sure.
And present to everyone. And move this over here. Okay, here we go. The spin of the Earth has never been proven. Never. The spin of the Earth has never been proven. In fact, Many tests have shown the opposite to be true. The Michelson-Morley experiment was set up to prove that heliocentricity was true. In fact, these tests proved, much to the dismay of Michelson, that the Earth did not move and was stationary. In 1729, James Bradley proved that the ether is not carried along with the Earth. In 1913, Sagnac proved that there was an ether, which destroys relativity, which says that there is no ether. In 1925, Michelson-Gale proved that the ether passed over the Earth every 24 hours. And in 1871, Airy's failure proved that the stars move, not the Earth, which allowed in 1887 the Michelson-Morley interferometer experiment to prove without a doubt that the Earth does not move. Did you learn about these experiments in school? Of course not. In fact, there is no experiment that has ever proved that the Earth moves, and many more that prove the opposite. Albert Einstein said, "Soon I came to the conclusion that our idea about the motion of the Earth with respect to the ether is incorrect if we admit Michelson's null result as a fact. This was the first path which led me to the special theory of relativity. Since then, I have come to believe that the motion of the Earth cannot be detected by any optical experiment, though the Earth is revolving around the sun." James A. Coleman said, "The easiest explanation was that the Earth was fixed in the ether and that everything else in the universe moved with respect to the Earth and the ether. Such an idea was not considered seriously, since it would mean in effect that our Earth occupied the omnipotent position in the universe, with all the other heavenly bodies paying homage and moving around it." Julian Barber said, "Thus, even now, 3.5 centuries after Galileo's condemnation by the Inquisition, it is still remarkably difficult to say categorically whether the Earth moves, and if so, in what precise sense." Stephen Hawking said, "So which is real, the Ptolemaic or the Copernican system? Although it is not uncommon for people to say that Copernicus proved Ptolemy wrong, that is not true. As in the case of our normal view versus that of the goldfish, one can use either picture as a model of the universe, for our observations of the heavens can be explained by assuming either that the Earth or the sun is at rest." And finally, George Ellis said, "People need to be aware that there is a range of models that could explain the observations. For instance, I can construct for you a spherically symmetrical universe with Earth at its center, and you cannot disprove it based on observations. You can only exclude it on philosophical grounds. What I want to bring into the open is the fact that we are using philosophical criteria in choosing our models. A lot of cosmology tries to hide that." So, they have made the Earth spin and orbit the sun, not through the scientific method, but through their ideology and desire to keep the Earth and its importance minimized as possible.
All right. Okay, so let me screen share, and turn on screen share, and then Keynote. Okay, the first thing I want to say is that a good portion of those quotes, when they talk about us or we or the Earth, they're referring to our solar system or even our galaxy. I don't think there is a single one of those quotes, like whether it was from Einstein or those other guys at the very end, where when they mentioned the word Earth, I don't think any of them was actually talking about the planet. I think they were talking about the solar system. Because,
why would you say that?
Because every single one of those guys is a heliocentrist. Okay.
This is what you need to understand. This is the problem, is that these guys are heliocentrists because they have entered a scientific foundation, or they've entered the scientific world. And in science, you cannot have a question that defers to a creator. You can't have a point where you say, oh, God is responsible for that, because science says there is nothing outside of physical nature. There is nothing that's controlling this. There is nothing that's organizing this, that it's a fluke accident. And that's something that was decided long, long ago. So when they had their observations, if one of the possibilities is the Earth at the center of the universe, it's immediately dismissed. It has to be categorically dismissed.
But the thing is, I think you're confusing Earth at the center of the universe with Earth's solar system at the center of the universe, or Earth's galaxy at the center of the universe. Because that's really what they're talking about is that they're talking about measuring galaxies that are, I think, 14 or maybe 17 billion light years away.
No, let's bring this all back. We're talking about the Earth here. Let's bring it all back. Before we get into that,
Sure.
Let's look at what Stephen Hawking said. So which is real, the Ptolemaic or the Copernican system? He said, although it's not uncommon for people to say that Copernicus proved Ptolemy wrong, Ptolemy put the Earth at the center, everything orbiting around it. Copernicus put the sun at the center, everything orbiting around it. And he says that is not true. As in the case of our normal view versus that of a goldfish, we can use either picture as a model of the universe. For our observations of the heavens can be explained by assuming either the Earth or the sun to be at rest. So he's not talking about anything other than the Earth can be taken as the center. It can be taken that everything moves around the Earth, or you can take the sun.
All right. So that Hawking quote, when he's specifically talking about Copernicus and Ptolemy. Okay. So he's talking about the planet Earth. Oh, by the way, he's talking about a globe planet Earth.
Understood.
But the thing is, you have these things, I guess they call them epicycles, where the retrograde motion of the planets in the sky, that were, they really, really, really tried hard to come up with models that describe these retrograde motions based upon an Earth-centered model. Okay. But it was and literally that was what they called geocentrism. It was a globe Earth, because they knew the Earth was a globe. It was a globe Earth with everything in the Earth, or everything in our solar system, including the sun, orbiting around it. But they just couldn't make sense of the observations. And so that's when the heliocentric model came in. But the thing is, you could still say, well, it could be either this or that. But as long as you go only out to the planets, because as soon as you start talking about the stars, that's when things get ridiculous, because they would be moving at, faster than light speeds.
But that's because they already had the idea that stars are suns, and that they must be of the size of the sun, and that everything stems from that.
Right.
But I mean, I didn't like what you said, because it's not, these quotes are each talking about the Earth. There's not one that's talking about anything different. When Julian Barber says 3.5 centuries after Galileo's condemnation by the Inquisition, it is still remarkably difficult to say categorically whether the Earth moves, and if so, in what sense? Because they're saying that there is no evidence, there is no proof that the Earth moves at all. The Earth, they're not talking about the solar system. They're not talking about this Milky Way galaxy. They are specifically talking about the fact that the Earth cannot be proven to be spinning or moving. That it is again, you can go to George Ellis when he says that people need to be aware that there's a range of models that can explain the observations, and then he ends it with, a lot of cosmology tries to hide that. That is a problem when we're talking about a scientific entity, a scientific enterprise, or a study, when you're saying that a lot of cosmology tries to hide that. See, what you're saying there is that a lot of science tries to hide something. That is the complete opposite of science. It is religion. If you're taking observations and then saying, well, it could be this or it could be that, but we're going to choose this one because it better suits our plans. It better suits our ideas. It's not that it better suits our observations. It's that it better suits, because science can't ever say, well, the Earth is the center of the universe, because the next question is why? Who put us here? Why are we here? What is the point of us being the center? And science knows that they can never answer that question, so they don't allow that question to ever come up. So instead, we have now a universe that makes no sense to anybody. That you said that physicists are still arguing about they're on the cutting edge. Yeah, because they're barking up the wrong tree.
What I would say is in terms of these cosmological questions about where the Earth is, and what I would argue is where say the Milky Way galaxy is that's the bleeding edge. That's the bleeding edge of cosmology right now. If you have a hand grenade, and you have an observer on one of the fragments, and so the hand grenade goes off, and all the fragments are going in opposite directions. Well, for that observer, all the fragments are going away from him, but to a third-party observer, that little one fragment, called Earth, is or called Milky Way galaxy, that's just moving away from a central point along with all the other fragments. So it's like you can't tell from observation. The observer on the fragment is going to, and so that's really what they're talking about. Because when we look out into the universe, and we see all these galaxies moving away from us, except for Andromeda. Andromeda is moving towards us. But we have this picture that, like, it looks like everything is moving away from us,
Right.
and also, how far can we see? We can only see as far as we can see. In other words, the universe appears to be a sphere with Earth at the center.
Correct.
So it's like, but what if Earth is not at the center? It's just it's a sphere with or Earth is the center. When I say Earth, I mean like the Milky Way galaxy, because that's as far as we can see. That's the limits of our seeing capability. So we are at, the phrase I like to use is, we are at the center of the observable universe, because it's sort of self-referential. We and observe. All right. And that's really the argument that these guys, Ellis and these guys are having, is that, on the one hand, you could say we're at the center of the observable universe. And so you could either argue we're at the center of the actual universe, or on the other hand, we're just at the center of what we can see. And that gets into a philosophical question. Because
if that's the truth, though, isn't the Big Bang then only applicable to us being at the center? Based on what you're saying that as far as we can see tells us these distances, and that's as far as we can see because that's our distance max. Well, then how do you explain how they know when the Big Bang took place, and they rewind it to the beginning and they know what happened a billionth of a second after?
Yeah.
How is all that possible?
That's, when they start talking about what happened 1/1000th of a second after the Big Bang, I mean, that's when my eyes
Why they have to do that?
Because it's like, how do they empirically know that, and who's going to prove them? Who's going to prove them wrong? No, it's not a billionth of a second. It's a millionth of a second. You idiot. It's like, how are they going to, decide who's right? So yeah,
well, because they needed everything that's in the universe. They needed it all created in a second. Well, not in a second, in a billionth of a second. So they're saying once everything was here, then this is what happened from there. But I mean, you're proving my point by saying it's a joke. It's a belief. It's a system of conjecture. It's not anything that can be empirically proven. Yet, if you say that the universe is 8 billion years old, you will have people laugh at you. If you say it's 6,000 years old, you'll have people laugh at you.
Sure.
It's clearly 14 billion years old, and the Earth is clearly 4.54 billion years old. These things are not facts by any stretch of the imagination. They are ideas that fit their particular model. And when you talk about these quotes by these guys, they're clearly saying, and that's why I still go back to that, they're clearly saying that there's a problem. And then I like what you said. You were describing the fact that no, they're saying that when they look out, they're seeing all these galaxies go away from them, and it's the same as the shrapnel from a grenade. That's true until you get to the point of the recent CMB findings, because when they look at the cosmic microwave background and they're measuring the amount of radiation hitting the Earth coming from all directions, they have basically realized that we are the center. That, I mean, Lawrence Krauss says, where do I have that quote right here? But when you look at the CMB map, you also see that the structure that is observed is, in fact, in a weird way, correlated with the plane of the Earth around the sun. Is this Copernicus coming back to haunt us? That's crazy. We're looking out at the whole universe. There's no way there should be a correlation of structure with our motion of the Earth around the sun, the plane of the Earth around the sun, the ecliptic. That would say that we truly are the center of the universe. That's what they're seeing now, but they can't go there. And that's my problem with science, is that they are not allowing themselves to, they're admitting that. He just admitted that there. George Ellis admits it. Max Tegmark admits it. These guys are seeing that, but they also understand that the structure that they currently operate in, the scientific world, the world of astronomy, doesn't allow that belief. So then they have to create all these other ideas around what is so simple, that we are the center, that everything's moving away from us, that there was a Big Bang, a moment of creation, and it started here at Earth. That's why there's the cosmic microwave background is the furthest that we can see. These are the things they're measuring, but because they're against the idea of us being the center, and everybody says it, from Hawking saying that they base it on modesty, to George Ellis saying it's a philosophical criteria in which they're choosing their model. That's what science is, and they should. I can't even get mad at them because they admit it. I get mad at people who won't allow that idea, or who simply dismiss it. I'm guessing like you are, by saying, oh, well, they're talking about the galaxy, or they're not. They're talking about the Earth.
Yeah, well, I'd have to see those exact quotes in context. But I will say this, Jaron, and I do have a couple slides that just deal with the spin of the Earth, is that these are these cosmological origin questions, whether the story of creation, like my wife believes in basically, what the mainstream science says, but she says, like, the Big Bang was, who says the Big Bang wasn't created by God? My wife is a devout believer in God, a higher power, and she says there's no contradiction there. What if God created the Big Bang? But I'm still going to call that the bleeding edge, and that people are going to argue over stuff at the bleeding edge. Whereas whether the Earth spins on its axis, that's not the bleeding edge. And so let me just go through a couple slides here, because I think you might be able to take a good bit of time on a nice long weekend and just clicking on the science background tab for this website. Are you familiar with International Earth Rotation and Reference Systems Service? Because it is these guys are so dry, it's not even funny. But basically, their service, it literally is a service. They've got a board of directors and annual meetings, etc., is to provide information for basically any agency that needs to know exact positions of the Earth and any place on the Earth with regards to the Earth's rotation. So everybody from astronomers to people who make GPS units to people who make satellites, they will consult with these guys over the Earth's rotation. And so I'm just presenting this to you
because I'm confused again. If we just read that they're saying that we cannot tell whether the Earth is moving or whether the universe is moving around it, then what these guys are doing, it could be the universe rotation service, correct? It would be
no, because what I would argue is that back to the cosmology stuff is they're talking about bigger picture. Like there's no doubt in any of those people's minds, whether it was Hawking, Einstein, Krauss, any of those people, there's no doubt in any of their minds that we live in a heliocentric solar system. Okay, a heliocentric solar system. The Earth spins on its axis, the Earth orbits the sun. In fact, one of those quotes talked about the Earth orbiting the sun. So it's like you're sort of quoting a guy that talks about the Earth orbiting the sun.
Einstein says one of the funniest things I've ever heard. He says that he came to the conclusion that our idea of the motion of the Earth cannot be measured by any optical experiment, though the Earth is revolving around the sun. That's because the whole model that they are operating under requires it.
Yeah. So, but if you read the context, like I actually have the book that quote came from, and I read,
right.
I read the whole chapter, and there's no denying that he, where his stance is, and what he's talking about is if you just were to set up a telescope and just look, then you can't say that the stars are moving overhead versus that the Earth is turning underneath our feet. Just looking, it's either one or the other, and you can't tell just by looking. That's what he was saying. Okay. Which was what brings me to the science background on this. It's the fourth tab over, science background, where it talks about how they actually measure the spin of the Earth. And it's very, very involved, but I wanted to put this out there because I know there's a bunch of people listening now who are, science-minded people who, love to kind of dig into the technical details, and it's, their methods of measuring the spin of the Earth, there's quite a cornucopia of techniques. It's not just, we look up in the sky and we see the stars move. It's a whole lot more than that. Now, I've got a little thought experiment for you. And this is no proof. So please, 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 and anybody listening, please don't say, oh, flat Earth math, he didn't prove anything. It's a thought experiment. It's something I want you to think of. So I'm going to put you in a swivel chair, and up in the sky is a chemtrail plane, Goodyear blimp, the moon, maybe even the sun, maybe planet Venus, clouds, and then a hawk that's soaring. And they're spinning you in this chair so fast that all you see everything swirling over your head. Okay. And I hope you understand, I hope you can visualize that everything that's going to be swirling over your head basically based on the axis of your swivel chair's spin. I mean, like, you're not going to tell if the jet's moving faster than the blimp or the cloud or the moon. Everything is just going to be spinning around you. All right. And in fact, if you were going horizontally, you've got these paths. If you were going sort of diagonally, you've got these paths. So getting back to this, if you were to take consecutive photos, like they're spinning you and you take a photo, and then they spin you again, they take a photo. And as you compare all these photos, you see, oh yes, I see the plane is moving, and I see the Goodyear blimp is drifting along, and I see the clouds are moving, and so you sense that these 5 objects are moving independently of each other, but they are all moving in the exact same, I'm going to call them sky grooves. Okay? Sky grooves. When you're spinning so fast, you can't tell the motion, the relative motion. Like the bird is flying in the same sky groove as the jet plane. But when you compare successive revolutions, you see that the jet is traveling on its trajectory and the bird is traveling on its trajectory, and they're clearly not connected, right? So here's the thing. And again, this doesn't prove that the Earth rotates. It's just a thought experiment. But if you're at the equator and you take a time-lapse photo of the stars, this is what you see. And if you take a photo, and I'm guessing this is near 30 degrees latitude based on the angle, this is what you see. And the thing is, some of those items could be planets. There could be planets in this scene. I don't know. So the idea is that everything is following sky grooves, and only if you took pictures day over day, you'd be able to see, oh, here's the planet, here's planet Mars, here's planet Venus, etc. I mean, even the sun and the moon are going through these sky grooves, which kind of indicates to me that we're the ones moving, right? So getting back to the swivel chair example, you could either say that the plane and the blimp and the moon are attached to each other and they're all spinning around me, or you could say I'm the one spinning. Mm-hmm. All right, it's just a thought experiment. That's all that is, and that's all I have to say about it.
And one weird thing about the star circles and the star trails, or sky grooves as you call them, is it's another thing that's run through a computer program that we only see 8 hours of night. So first of all, any star can only do a third of a circle. Yet you see star trails look like they're doing circles in the sky. And what that does is it forces people at home to say, well, we see the stars going around in a circle. And they assume that that's what we see. They see, oh, well, you can look at these star trails and they're all showing circles around the middle point. That therefore they're doing that. But we don't actually see that. We only see a third of the night. We only see a third of the day. So a star can only do a third of a circle. So everything else is done by a computer program.
Well, I'm going to interject here. So okay. If you take we just had the winter solstice. If you're doing any sky watching on the winter solstice, you have well over 12 hours, depending on your latitude. The further north you go, 12 hours of night, 13 hours of night. And then if you get up to the Arctic Circle, you will have 24 hours of night. So you can absolutely observe longer than a third. I mean, just literally from your backyard, you're near San Francisco. I would say that on the winter solstice, you would probably have 12 hours of darkness. So I do understand your point that we see, we say we see circles. We don't see circles. We see arcs. But you put all the arcs together, and they make 1,000 fractions of a circle, which puts together a picture of a central point. So, I mean, I kind of agree with you and disagree with you at the same time. But
yeah, and I mean, if it's just north, if they look at the flat Earth idea, and you're looking up at the stars, which are rotating, let's say they're all connected to a plane that's rotating above your head, that the same thing as star trails would happen. That you're looking up at the rotating disk above your head, and it's going to, if you just took a time lapse of it, make a third of a circle, which then put in through a computer program is going to show you a circle around that central star.
Yes, I agree with you, but everybody on the flat Earth would see the exact same image. They would all see stars rotating around Polaris, but Polaris would not be dependent on latitude, and they would never see this image, the image that I've got on the screen right now. If the Earth were a flat plane, nobody would ever see this image unless everybody saw this image.
No, okay. So let's
you can't just have a dome and have the dome rotate. You would never see this.
So if you were to take your bedroom, okay, where the room that you're in now, and now multiply that out so it's as big as your city. Okay, I don't know where you live, but take your room and you're just going to make it so big that it's as big as your city. But you're going to keep that roof or the ceiling of the room at the same height. So when you look off into the distance, how quickly will the ceiling hit the floor? Meaning, if there's let's say you have I don't know, a big spider, okay, as big as you are, and it's on the roof, it's on the ceiling above your head, and that spider starts crawling away from you. Okay, it's going away from you. How quickly would you lose that spider due to perspective? How quickly would that spider meet the floor?
It would never. Well, if it would hit the floor, it would be at the vanishing point, but
Correct.
it would never go past the floor. It would never. And the thing is, and you could do this. Perspective is another topic, and we're at 1 hour and 45 minutes.
Okay.
Perspective is another topic entirely. The thing is, you would see the spider go slower and slower and slower as it got further and further away from you. And then it would disappear into a tiny speck. You wouldn't just see it just moving down and then intersecting with the floor. That's not how perspective works.
Well,
so when we see
these that small, yes, but when you're talking if you want it bigger, then that's a different.
But when we see these stars, you can actually measure their speed using backyard instruments. I haven't gotten to that video yet. I'm still only about halfway through my series, but I'm going to spend a whole lot of time on the stars, and I'm going to actually teach people how to measure the speed of the stars, and they will not change speed from when they're overhead to when they're at the horizon. They will not change speed, which means that it is not a matter of perspective to see the stars are actually setting. It looks like we're either looking due east or due west, depending on what hemisphere we're in. Mm-hmm. But yeah, it's an interesting puzzle to take your observations. Like, for example, you could literally put a protractor up against the screen, and you can actually figure out what latitude this photo was taken at. And that just doesn't make any sense on any flat Earth model. But if let's take a flat Earth model and just say somebody's standing at the North Pole looking straight up at the North Star, right? Sure.
Okay, so then as you moved away from the North Pole, the angle that you're looking at Polaris would change equal with your distance away from the North Pole.
No, not equal. It would change. The angle would change, absolutely. But if you moved, if you moved, like let's say the equator was, we're going to call it 90 units away, for 90 degrees, you'd still be looking up. When you move to the equator 90 units away, you would still be looking up at Polaris. Polaris would not move 90 degrees in the sky, because then Polaris would be at the horizon. Well, now on the globe, when you're at the equator, Polaris is at the horizon. It has moved 90 degrees. It's a 1-to-1 ratio when you look at the globe Earth geometry. It is not a 1-to-1 ratio when you look at a flat geometry. It's a matter of drawing triangles and measuring the angles. If you keep going further away from the North Pole, yes, the Polaris will appear lower and lower in your sky, but not in a linear fashion. It won't. If you move 10 degrees away from the North Pole, Polaris doesn't decrease in altitude 10 degrees. It's absolutely not correlated.
But it does. It does by our measurements and observations.
Well, that's because we're on a globe. Okay, so Polaris has a exact 1-to-1 ratio of you move 10 degrees away from the North Pole, Polaris moves in the sky 10 degrees. Because that is only possible on a globe. And then as soon as you go 10 degrees south of the equator, now Polaris is 10 degrees south of your horizon. That is absolutely not, that geometry, that whole geometry does not make any sense on a flat Earth model.
Okay, but you're saying that then when we're triangulating that distance or that angle, are we taking into account that there is a curved baseline?
Yes, because you're measuring from the curve. You're measuring you're measuring from the baseline, from the surface of the sphere. Let me see. Am I still? Is
that how triangles work? That you can, if we take a 90-degree triangle, okay, so it's got a flat baseline. As soon as you tell me that we're at a 90-degree triangle, a right triangle, well, we just said that means that there's a 90-degree box there in the corner. So, and then you were to draw the line from the top of your line, say where Polaris is, down to where your next observer is. Well, you just created a triangle, but not a spherical triangle.
Sure. So I get what you're saying. So what you do is you take where you're standing right now and you make that a flat piece of the triangle, a flat, or at least a part of the angle of the triangle. You measure an angle from your surface. So am I still sharing? Can you see this? This was not Polaris. So Polaris would be straight up. But this is actually aiming to the right, but you could just turn your head and just call this Polaris. So if you were just to tilt this diagram and just imagine that Polaris is to our right, the angles still work the same. So we have these different measurements, and as these lines are aiming towards this thing that's very distant to our right, the angle does change with the surface of the circle, or with the angle on the circle. And this was taken from school kids' measurements, so there are a couple degrees off. But that's the idea, is that it's going to be a 1-to-1. You move 10 degrees up because your angle is going 10 degrees up, and then you're going to look at Polaris 10 degrees lower in the horizon. But anyway, I totally wasn't planning on showing this. But so we're almost at the 2-hour mark. We're 8 minutes shy of 2 hours. Do you want to move on to?
Let's go to the next one then, so we can finish them off. Let me get my thing back up. Okay, and I'm going to share. Present to everyone and share. Okay, and we'll go to the last one here. And lastly, number 1, 'tis the season to be folly. The seasons, as explained by heliocentrists, are extremely flawed. If our seasons do in fact come from the tilt of the Earth as we orbit the sun, then there's quite a few things we'd expect to see that we don't. First, during the southern summer, it is the rays hitting the north at a greater angle and the south getting more sun, hence it is their summer. But why then is there a frozen continent at the bottom of the globe, while in the north there's nothing but a pool of water? Because during the northern summer, the same thing but opposite happens. The north is getting the greater sun, as the south is getting the higher angled sun. Why then do we have this pool of water and no North Pole ice cap? So if, as we are taught, the tilt led to the seasons, then north and south would be the same. Also, we would expect to see hotter temperatures on Earth in the south. Why, do you ask? Well, there's a little known fact in the heliocentric model that the Earth is actually closer to the sun during the southern summer. Yes, that's right. If you live in the north, during your winter, the sun is closer to the Earth. By how much? By 375 Earth diameters. So we should see signs that the south is slightly warmer than the north. Well, do we see any signs of this 375 Earth diameter difference? The south has a frozen continent. The north does not. The north has 14 of the hottest 15 temperatures of all time. Lastly, let's take a look at the difference between 70 degrees north and 70 degrees south. Virtually, they should be close to identical. If anything, the south should be slightly warmer and more nurturing for life. We should see comparable temperatures, seasonal changes, length of day, plant and animal life, and the fact that there is so different of a selection of animals and plants tells us the globe model has major faults. In the north, we get warm summers. The southern summer does nothing to change Antarctica. The south has eternal winter, and the snow never melts. As far north as you can go, you'll find birds, reindeers, squirrels, rabbits, insects, and all decorated with plants, shrubs, flowers, and more. Within 70 degrees south, no plant, insect, or bird is found. At 49 degrees south, only 18 species of plant exist. If you go to 65 degrees north, which is 16 degrees further from the equator north, you can find Iceland, which alone has 870 species of plant. On the Isle of Georgia, at 54 degrees south, same latitude as England in the north, where forests, shrubs, and all kinds of plants and flowers exist. Captain Cook said there was not a bush or shrub to even make a toothpick. And beyond 70 degrees south, no plants, flowers, or trees exist. And again, 14 of the top 15 temperatures of all time are found in the north, not the south. So, there you have it. 5 facts about the Earth we didn't learn at school. Alrighty. So, go ahead. It's on.
Is that your phone ringing?
It is. I'm shutting it off.
Okay. So, let me present a little bit. Okay, share. Okay, 'tis the seasons. So the idea that we are closer to the sun in one season versus another, that's valid if you look at the actual values involved. And I think when we're at perihelion, we're something like 4% closer or if I'm not mistaken, which
3
is a
million.
very, very small. It's a very small amount.
Plus
So
3 million miles, 375 Earth diameters. So we can say it's a small amount.
Well, the thing is, 375 Earth diameters is a huge amount in terms of Earth diameters. In terms of percent, and that's really what I like to get back to with a lot of the flat Earth debate is, the people don't take the magnitude of numbers. If I could have one word, that word is magnitude. If I get people to think about magnitude of numbers, then a lot of these things would be solved. So what's the magnitude? Like, for example, the Earth is an oblate spheroid. What's the magnitude? Does it look like a squashed basketball, or is it only 0.3% squashed? What's the magnitude? So here we have a solar panel, and like everybody who's seen solar panels, that they don't mount them flat. They mount them at an angle, and it's not because of the top, getting the top a couple feet or a couple inches closer to the sun. It's to get the direct rays. And so it's a very, very simple equation. The sine of the angle equals the multiplier. So, if you have the direct rays shown on the left side of the screen with A, you have the exact same width of sunbeam at B, and it's covering a greater area. So that means you're getting less, you get less energy efficiency. And that's really the cause of our, not only the seasons because of the changing tilt of the Earth, effective tilt, but also the polar regions are a lot colder. So it is absolutely 100%. The seasons are due to the change of the angle of the sun, and not due to the distance of the sun. Now, the thing is, you raised a very good point. In our northern winter, we're closer to the sun. In the southern summer, they're closer. So they should have hotter summers, so to speak. But that's only if you eliminate all the other factors. If you look at a globe, you find that the vast majority of the Earth's surface is north of the equator. Like the massive continents are north of the equator, especially as you get into higher latitudes. If you get into the lower latitudes, I mean, the 30 degrees latitude runs right through the middle of Australia. So Australia is half in the tropics, not half, but I mean, it's a good portion of Australia is tropical, and that's the last continent you have before you get to Antarctica. Mm-hmm. So, what'd you say?
I said, mm-hmm.
Okay. So this is just and again, this is not proof, but when I saw this is literally taking a picture of my car. So I came out one morning, and this is a couple weeks ago, and it was, below freezing, but the sun had just started to rise. Mm-hmm. So the sun was very low on the horizon to my left. So my whole car was the same temperature, okay? Because literally it's been outside all night. My car was the same temperature. I hadn't opened the door. I hadn't turned on the engine. Mm-hmm. But the sun was at direct rays to the window, the side window. So you can't see from this picture, but it was due. I should have run my finger along it so you could see the dewdrops. But meanwhile, the windshield and the roof of my car was still in frost. Mm-hmm. Okay, and so I have a little diagram there. So it's all about the angle of the sun. Now,
so if you tilted the roof of your car towards the sun,
yes,
you tilted your car up on its two wheels.
Yes.
Then that frost wouldn't be there, correct? Because it would be getting the direct rays.
Oh, and this is something like I'm always about, don't believe me, don't believe a word I say, test it yourself. So you could literally go out with one of those like laser temperature, it's an infrared temperature sensor with a laser beam, and you could go out to a parking lot and any time of day, and then take temperature readings, like pick a color car, I don't know, a green colored car, mm-hmm. and then take temperature readings on the roof of the car, on the side of the car, assuming that car has been there, for over an hour or something, so it's had time, because the driver might have just pulled in.
Right.
But basically aim your temperature your gauge to the car at various places, and you figure, the room temperature, the air temperature is constant, but the surface angle to the sun will be varying, and then you will literally measure these variances.
So if that's true, though, if we tilt the car up and now it's got the better angles at the sun, then that frost wouldn't be there.
Yes.
So when it's the South summer and you've got the angles of the sun hitting Antarctica for basically 4 months, nonstop, direct rays, closer to the Earth than when it's the northern summer, yet we've got a frozen continent that never melts, that never brings life, that never is equal to its northern counterpart. So what I'm saying is, what you're again describing my point exactly. That why would it be different in the north and the south?
Okay, so there are more parts to the story than just the angle of the sun. So if everything were equal, Antarctica, 72 degrees south latitude should be exactly the same temperature as 72 degrees north latitude. Okay, all things being equal. But then we have these other elements, and that is that Antarctica is the highest continent on Earth. I mean, like literally, Antarctica is the highest continent. So the average elevation is, I don't know, 1.5 miles. The elevation of the South Pole is close to 2 miles. The highest point on the ice cap is like 2.5 miles. I mean, and they didn't say a mountaintop. They said ice cap. So they're talking about a flat surface of ice that is literally 2.5 miles high. And what do we know happens with altitude? We get decreased temperatures. So there's this concept called the tree line. And so I just looked up, this is from the Wikipedia entry on the tree line. And so when you get to middle latitudes, like say 45 degrees north latitude, the tree line is almost 2 miles up, 6,900 feet. But when you have higher latitudes, 69 degrees north latitude, the tree line is less than 2,000 feet. Okay, so when you get up even higher latitudes or lower latitudes, the Antarctica is, in the 70s, 80s, 90s, south latitude. That means their tree line is going to be, close to 1,000 feet or less than 1,000 feet, whereas the entire continent is well above that. So the point that I'm trying to make is,
okay, I get what you're saying.
Yeah. The other thing about this ice sheet is that it's not just a matter of latitude, because the ice sheet is so huge. It's the biggest ice sheet on Earth, that it extends further to lower latitudes than most other ice sheets. I mean, we have glaciers other places in the world, but Antarctica, basically, it's the ice sheet moves in all directions, like towards the coast. So when you get to the coast, what do you get? You just get a big pile of icebergs. You're not going to get any soil. You're not going to get any land that you could plant a tree. Okay, so in analyzing the flora and fauna of Antarctica, you have to take these things into account. But I was just amazed when I found out that most of Antarctica is 1.5 miles high. So this is an interesting picture, because this is actually, I think, 1 degree. It's 1.5 degrees away from the equator, and they actually call this the highest point on the Earth's surface, higher than Mount Everest, because the Earth is an oblate spheroid. This is actually closer to the sun than Mount Everest. And so what do we see at the very top? Even though it's closest to the sun, we see snow, because of the tree line. It's just an interesting anecdote. Now, this, I think, is going to not impress you, but it's not about latitude. So what I did is I picked 3 cities that all had 51 degrees north latitude: London, England, Astana, Kazakhstan, and Calgary in Alberta, Canada. And the thing I just want you to pay attention to is the low temperature. So the low temperature, and this is for the whole month of, say, January, it's like 45 degrees in London, 45 degrees Fahrenheit. Right. And that's, of course, they have their exceptions, but this is just an average. But meanwhile, in Kazakhstan, which is in the middle of a continent, we have, well below freezing, like, around 8 degrees Fahrenheit. And so, but they're both at 51 degrees north latitude. And not only that, they're only a few, maybe 1,000 miles east to west from each other. They're at the same latitude, but they have a huge difference in temperature. And the reason why is because we have more things that cause, flora and fauna to be able to go further north, such as these currents. Like on the United States, on the east coast of the United States, we call it the Gulf Stream, but the Gulf Stream kind of turns into the North Atlantic Current. And that's why the United Kingdom has much more temperate climates than it should based on its latitude alone. I was looking at the United Kingdom and what degrees of latitude the United Kingdom was at, and the state in the U.S. that coincides with that is Alaska. Granted, it's the southernmost reaches of Alaska. but like all of the UK is north of Maine, and Maine is the coldest of our continental states. I mean, it gets bitter cold in Maine, and the UK is even north of that. So the point I'm trying to make about your flora and fauna is that you're going to have much warmer climates, much more opportunity for wildlife to grow.
So where do you think those currents came from?
That's an oceanographer question. I have no clue.
That's what I'm saying. When we're trying to explain everything as right now the Iceland is Antarctica has got the highest land mass, as far as altitude, and we're explaining things right now.
Sure,
but they had to become that way by some sort of method.
Right, but there's a big difference between explaining the why and describing what we can measure. So, for example, the North Atlantic Current does exist. It has been measured for hundreds of years. Okay, why does it happen? I don't know. I mean, I'm sure oceanographers have good theories about it. Maybe they have the quote unquote the answer, and it's in their textbooks. I don't know. I do know that it does exist. And that if it didn't exist, the UK would have weather, much closer to Alaska's. But here's a tool that I think everybody should know. If you want to make your own equidistant azimuthal map, if you go to this website, ns6t.net, and if Globebusters Bob is listening, this guy is a ham radio operator. Obviously, that's his ham radio. I don't know what you call those things. Call sign or whatever. And so if you type in, I guess it's like 90,0, or and I put in 90,90, but basically 90 degrees north latitude. And then you don't put in anything for the distance. Like, you literally can make your own Gleason's map. Right. Now, what I did is I put in different distances. I think radius of 5,000 kilometers, and I just wanted to compare Antarctica with, say, the North Pole. Now, you called the North Pole, a big pool of water, but it's a big pool of water that's at sea level, whereas that North Pole on the left-hand screen is 1.5 miles up in elevation. Hence all the ice. But the thing, and I don't know, can you see my mouse, like, as my mouse is moving around? So there's all this continent, like here's Asia, and I was just informed that Europe was not a continent, but basically Eurasia. And so as my mouse is going around here in Eurasia, basically anybody that wants to go north can walk there, like caribou or reindeer, they could literally just walk north. Whereas if you go the same latitude on the Antarctic map, we're now thousands of miles. We're going to get no caribou that are going to swim thousands of miles to go to a colder place. Right. Okay. And so
that argument is the same if you were to look at the flat Earth map. The flat Earth azimuthal map, right? If you go back one slide,
okay,
and you say the same thing. Animals are going to definitely live in the middle there. They can go between the continents. They can migrate. They're closer to the sun. There's more climate that's hospitable for them. Whereas the outskirts, who's going to go swim to the outskirts?
Sure.
When you look at a globe and you say, well, why would there be this 2-mile high ice cap at the South Pole? It makes no sense. It does not fit any globe model when you're saying, oh, well, centrifugal force would cause this. It should have all the water at the center, not around the bottom. There shouldn't be a bottom ice cap. Why are these things existing when, if you look at the azimuthal and you say it's the outside, now things make sense. We've got a 2-mile high outskirt of ice mountains that surrounds the Earth, holds the water in. It simply makes sense on a flat Earth, where on a globe you're having to come up with a million different reasons for it.
Well, okay, so I could totally understand the ice wall keeps the water in. There is no edge. Like the big waterfall on the that Kansas cover, Point of No Return, that album from I don't know, late 1970s. I totally get that, but when you say that it makes no sense that Antarctica would be so high, I believe that they say Antarctica is so high because they're measuring it from the ice cap. They're not measuring the actual from the continent, from the bedrock down below. So if you eliminated, like, let's say if you just took Antarctica and you just stuck it on the equator, melted all the ice, I don't believe it would be the highest continent anymore. Okay. So I think it's only the highest continent because it is a landmass that does gather snow, unlike the North Pole, which is, it's just going to be sea ice. Any snow that falls at the North Pole is just going to turn into sea ice versus an ice pack on Antarctica. But the point behind these slides.
Hold on, explain again for me. Why don't they just measure everything from sea level? So Antarctica is 2 miles above sea level.
Well, no. What I'm saying is, when they say it's the highest continent, that quote back here, Antarctica is the highest continent on Earth, average elevation. When they say the average elevation, I think they're measuring from the surface of the ice cap. I don't think, and I don't know, but maybe I'm wrong. Okay, but my whole point behind the slideshow, these series of slides, is to explain that when you talk about flora and fauna and how come there aren't as much flora and fauna so far south as there is that far north, is that you've got essentially a land bridge. I mean, any flora and fauna could simply walk there. Whereas, and I think there's measurements on this, it's 600 miles away from South America. It's 2,500 miles from Australia and 2,500 miles away from Africa. So it's a really, really far way to go. And you're not going to go there if you're just going to find a bunch of ice, right. Nothing grows in ice.
So where did it come from? Why is it there?
Well, that's for the geologists. And the thing is, geologists
we're told a certain story about the seasons of Earth, and we can tell based on astronomical measurements and everything that how long it's been the way it's been, as far as the North Pole during the North summer is pointed at the sun, the South Pole is pointed at the sun during its summer. And the fact that it's a little bit closer, maybe you say that doesn't make a difference. I'll just say it should make a little difference. I mean, if I go 2,000 feet high, I'll get a sunburn a lot faster than from the sea level. That's because I'm getting closer to the sun.
No, it's not because you're getting closer to the sun. You're eliminating your layers. The air is thinner. You're eliminating. I mean, the air that we breathe actually has an insulating effect in terms of thermal radiation. Not thermal, solar radiation.
I'm not saying that I know that at the equator there's mountains that have snow on the top. I'm not saying because they're closer to the sun they're going to be hotter, more tropical temperatures. But the fact that I get a sunburn easier, what's the reason for that?
Yeah, I think that's a matter of the thickness of the atmosphere. The atmosphere is thickest down below. So when you go through to where the atmosphere is thinner, you've got less of a protection. That's not an area of my expertise, but that's just that's my impression.
Okay. My whole problem with what you're describing is fine, but
just let me finish this point. If you go up to the top of, say, a 5,000 foot tall mountain and you get a sunburn easier, it is completely unreasonable, even on a flat Earth model where the sun is possibly 3,000 miles high. 3,000 miles minus one, you're at the top of a mile tall mountain. 3,000 miles minus one does not, that's a rounding error.
3,000 miles high. So
well, but I mean, a lot of the flat Earth models say a 3,000 mile high sun.
Sure.
I mean, unless you want to say that it's 50 miles high, in which case, now you're a mile closer. But
50 miles would be definitely closer to my opinion. But
yeah, okay.
Because we can see from watching balloon footage that the sun never appears much higher than the balloon. Maybe it's double, maybe it's triple. 300,000 feet wouldn't be a stretch. What is that, about 50 miles?
It all depends on the time of day that the balloon launch was launched. There was that dawn launch from either Dwayne Kellum did it, where you would actually see the sunrise at the very end of the balloon flight, so therefore the sun is lower than the balloon, and the balloon's only up 10 miles. So,
well, that's a perspective thing, but yes.
Yeah. So we're at 2 hours and 15 minutes. Okay. So, because I'd love to talk to you all night, but in the interest of our audience,
no, I mean, my thing is that I think you showed it well. That what I'm looking at is that it comes down to these things that you're claiming. I'm arguing from a position of incredulity, whereas I'm saying I'm doubting what I'm told, and the way science works, that's part of being a skeptic. That's part of science, is doubting the current going belief. And when you doubt it, you should be given evidence, or you should be able to look at examples or experiments or research that shows what science has agreed to be the fact. And I don't think that that's the case in any of these. Starting with the speed of the Earth, we're not given any evidence that we are moving at those speeds other than, well, our math says so, right?
This
and then
true.
we look at each one and they don't make sense. It doesn't make sense when they say, oh, it's a big old wives' tale that the Earth was ever flat. They thought from 500 BC that it was a ball, and all the way till we have our first globe in 1500. So you're talking about almost 2,000 years of humans not being able. You guys give them all the credit in the world. They measured angles of the sun. They discovered all these things. They discovered mathematics, created calculus, but they couldn't figure out how to map the Earth on a ball, even though they knew it was a ball. And that would be the most obvious next step. Hey, let's take the Earth and what we know about it and put it on this sphere, since we live on a sphere. But that's not the case. We don't find that. There's nothing till 1492. It's as if Columbus sailing to America led them to believe, oh, there's another side of the Earth. Now we need to draw this ball. Now we're going to start making the globe. And then everything comes from there. So it certainly seems like what we were taught as kids is more in line with the truth than what they're trying to backstep now. And the reason for that is they don't want anybody to think that anybody ever thought the Earth is flat. And these are the things I'm telling you. They want to cut that off. They want to call it stupid. They want to call it ancient desert wandering belief. They want to say it has no basis in fact. Flat earthers are idiots. This is a direction from science. This is a direction from Bill Nye. This is a direction from Neil deGrasse. These guys are pushing the idea that you are not with the times. You're not a current person if you believe at all in the flat earth. Not because of evidence, but because it's stupid. It's ancient. We've known this for thousands of years, the Coriolis effect. So I'm just saying, it looks to me as a story. It doesn't look like it's truth. And if it was with truth, you wouldn't care that anybody, but it's like all these people, you've seen them. How angry are people that I'm talking about flat earth? It is sent some people into a rage. And the reason for that is because they simply don't want to face the fact that maybe they were lied to. I mean, I know it's kind of hard speaking to you because I know that you believe in everything mainstream.
I do not believe in anything mainstream.
Okay,
oh my goodness gracious.
Name one thing you don't believe in, or name one thing mainstream that's an original thought. Tell me an original thought that you have.
An original thought that Waco, you know, the ATF murdered those people in Waco. Okay. You know, that the drug war should be ended tomorrow. And that literally 100% of crimes dealing with possession, selling, distribution of drugs should be eliminated. And I mean that very sincerely. Literally legalize 100%. Every drug that's on the market today on the streets, it should be legalized 100%.
I feel like that is an original thought. That's not by Wikipedia. That's not a mainstream belief. But you... that's good. I'm glad that you feel that, because I sometimes find people that simply can't believe something until science says it's okay, or until the news media says that's okay. And you just said two things that certainly the news media wouldn't say the truth.
So here you talk about stories. Like, what if these things are stories? I mean, stories could have shades of the truth. They could be mostly true. I mean, we all see these movies based on a true story, and it turns out it has the word "the" in the title, you know, like Fargo. Right. Fargo, based on a true story. Yes, there is a town called Fargo. You know, that's the true story. So all right, so it's a story. But then you also have guys like Robotham and Winship and you know, going back into all the classic flat earthers. What if they're telling stories? You know, the ice wall, that's a story, you know, the story of the ice wall. So why don't we say, let's throw all of it out the window. Let's throw NASA under the bus, you know, throw everybody under the bus. They're all liars. They're all telling stories. And let's get outside and make measurements. Let's get outside and make measurements. And that is my philosophy. And that, because I just came up with this thing. It took me 2 weeks, but I came up with a way of predicting the angle of sunrise. You know, in other words, is it due east? Is it a little bit south of due east? You know, and so it's like I've made a prediction. That prediction is based on a certain set of mathematics. So, you know, get outside and make measurements.
You don't think you're swayed by the current going belief?
Oh, well, no. I mean, the thing is, the current going belief is the heliocentric model, and Correct. So what I do is I base my mathematics on the heliocentric model. I also base mathematics on Robotham's, you know, the classic model of, you know, if you and I've got the book right here, the Zetetic Astronomy. I don't know if you can see this. I'm not sure if I'm presenting. So, I've got my reading list. I've got the greatest lie on Earth, and I've got Zetetic Cosmogony. So basically you take these guys' models and you put them together, and then so I run the math based on those models. And you can predict the sunrise there as well. You can have the new Globebusters map. You can predict the sunrise based on the new Globebusters map. I tell people how they can do that based upon the time of sunrise and sunset, and you can kind of run the angles. And so that's my whole point is get outside, forget NASA, forget Bill Nye. I can't stand. Oh, here's a mainstream thought for you. I hate Bill Nye and I hate Neil deGrasse Tyson. Okay. I can't stand either of them. They are so smug, arrogant. And then global warming. Okay. There's a mainstream thing. Global warming is a government hoax. Okay.
Wow. I'm shocked.
And that's one of the biggest reasons why I can't stand Bill Nye and Neil deGrasse Tyson. But also, they're both very smug. They're so know-it-all. Oh my goodness, I want to smack them. But anyway, get outside and make your own measurements. Because what I hear all the time is that you can't measure the heights of things, and I'm like, okay, so measure the height and then just play with the numbers. Measure the height and then see what the numbers say. And people might be surprised at what they find. So anyway,
that's saying we can measure the curvature.
Well, the curvature is extremely tough to measure because the planet is so huge, but you can detect the effects of curvature. So I detailed this in over 16 minutes in my debate with Jibby Jedi. Okay. My first 2 points one was how do you see the curvature? 2 was how do you detect the effects of curvature in my debate with Jibby Jedi. And it is possible. It's possible to see the curvature. It's possible to detect the effects of curvature, but it's very hard to do. One thing that's interesting in the Zeteticism, I don't know if I can show this. This picture, this is Zetetic Astronomy. This is Robotham's book.
From the canal.
This is the second Bedford level experiment. And that horizontal line was the level line. In other words, the bridge and this disc are both below eye level, and the disc is above the bridge. So we were sighting in the telescope from 13 feet above the water to a bridge that was also 13 feet above the water, and that disc was also 13 feet above the water. This is detecting the effects of curvature, and for some reason, this guy doesn't believe it. Parallax.
Well, let me explain to you why, because I think you don't understand that experiment. If you take a telescope and you were to set it at your eye height, so 6 feet, okay, and you were to look off in the distance, well, whatever you're looking at is going to get smaller and smaller and smaller. A tree, a telephone pole, whatever, till it gets to the horizon line, right?
Yes.
But your telescope is set at your 6 feet tall. So do you think that the crosshairs of that telescope are going to meet the horizon line, or do you think they're going to be above that?
They're going to be above it,
right? So
but they're going to be 6 feet above it. But what you don't understand, Jaron, is that the numbers they were dealing with was like 13 feet 6 inches or something. It was 13 feet. Okay, right. So they were up on the telescope was literally on one bridge, right? And then they had this post that was at the 3 mile mark, and the post had a disc on it, and the disc was exactly 13 feet high, or exactly the same height as the telescope. And then on the far bridge, they mounted a cloth banner with a big black stripe on it, and it was also exactly 13, or the same distance. It was the same height above the water. And we all know that the water, water finds its level. So that's how it was. They were able to calibrate everything to the water level, and it was a non-moving body of water. So we have 13 feet, 13 feet, 13 feet. It should be a straight line, but for some reason, the disc was higher than that line. And not only that, but the disc was actually below the level line because it wasn't just a telescope. It was actually a surveying level that has this internal leveling mechanism. Mm-hmm. So not only was the disc below level, but the bridge was below level, and then the disc was higher than the bridge. So that's a clear, but did you not open and shut, but that's a clear evidence of curvature.
Did you read the book? Did you read where he explains the reason why that result is incorrect?
He explains it away using a lot of hand wavy gestures. I didn't see him wave his hands, but he explains it away. And good for him for including that experiment. But he does just explain it away. I don't think he understood what that thing was really showing, or what it should have shown. Because in the first edition of that book, they showed like a row of flags, and they said, you should look straight across in this row of flags. But this was a later edition, which was after Wallace did his experiment at the Bedford level.
Let me share my screen because I want to. We'll just finish on that because that's a good point.
Okay.
Am I sharing it?
It says I'm still presenting. Okay, I see it. Yes.
If you're still presenting, let me turn it off.
No, I see your screen.
Okay, good. Oops.
I don't see your screen. There you go.
Okay, here. This image here, let me see if I can get it bigger, is the same thing. The same thing you're talking about. Hopefully, you can see that.
Yes, with the red posts.
Yeah, if we're looking at these red posts and they were to be going down towards the horizon, if you set up a telescope at the top post here, okay, and you leveled it, do you think that the line the telescope would see would go down these red tops?
If those railroad tracks were absolutely the same as sea level, like there was a canal nearby and we could maintain that, those red tops, then the red posts would go down, that they would decrease. They would not stay level with the telescope over a period of miles. They would not stay level with the telescope. They would drop below, not just due to perspective, right? But they would literally drop below the level of that.
Correct.
Of that level line.
But you just showed a picture of a bridge and the post below the level line, and you're explaining that away by saying that the Earth curves. But that's not the case.
No, but the reason, Jaron, I think you misunderstood when you asked me about these red posts. The reason why I'm saying that they're going to go down is because the Earth curves. Okay, it's not because they're just getting far away. Like if you put these red posts over say 100 yards, that they're not going to go down. Okay, but if you have the red posts over 6 miles, yes, they're going to go down because of the curvature of the Earth. That was my point.
Okay, so if we wanted to do a test to prove whether that was the case or not, and we just looked at a short distance from here to this fourth post.
Say, call it 100 yards.
Call it 100 yards, and there's 4 posts, each at 25 yards. If you were to line a telescope up and you were to level it with the first one, if you didn't look into your viewfinder and make sure that the second one was also leveled, then your telescope view is just an increased view of the first one. Meaning you're just going to zoom in. That's all a telescope does, is zoom in on that point.
Sure.
So it wouldn't be level. So I'm saying,
well, no. I mean, if you had a leveling telescope, and I don't know if you know how the construction level works, but it has an internal mechanism. It's with mirrors and it's got it's a correcting mechanism. It's not just a carpenter's level with the bubble. There's an actual mechanical element inside the it's called a construction level. Right. So I mean, when you have that line, that horizontal line, that is dead nuts level to where the telescope is. Okay, but over 100 yards, it's not going to be too appreciable.
Okay, so if you looked into something, okay, so even though at 3 miles you're supposed to drop what? So 8, then 32. What is the? I don't know what it is at 3 miles.
Yeah, well, it's 6 feet. It's 6 feet, but that's actually which is also the sagitta for 6 miles. Okay, so 3 miles you should drop 6 feet, but that's Now,
don't you think that's based off of the fact that you're looking from 6 feet down to the horizon line?
No, but you're not looking down. You're looking in the general direction of the horizon, but you're looking level. You're looking level, so your horizon is literally going to be lower than your instrument. Right. I mean, obviously, because you're on a tripod.
You're blaming that on the curvature of the Earth, though.
Well, but it's actually accelerating. The thing is, if you have these red posts and they're all the same height, if you saw a red post in the middle, like if you focused your telescope from the first red post to the last red post, and you saw a red post in the middle higher, wouldn't that tell you something strange? Like it's not a straight line. It's actually a
right. So when did that happen?
It gets higher. That's what the Wallace experiment that I showed you on the diagram. They were focusing. The telescope was 13 feet up. The banner on the bridge, it was like a big black line, was 13 feet up, and the disc was 13 feet up. And they saw the disc was 5 feet higher then because there was a disc and it was like a square and a circle or something, and it was actually 5 feet higher than it should have been.
Then the banner.
When they sighted at the banner, when you look from the bridge to the banner, make a straight line from the bridge to the banner, right? The post was higher in the middle. I mean, this is a crazy drawing because the posts are kind of floating in the air. But
well, yeah, this one's kind of ridiculous. This is what Armored Skeptic said happened in that experiment, which I totally
it was kind of a silly. I don't
think he quite understood the experiment. Yeah. But I guess I'm still thinking you don't quite understand it either, because you're saying that if this view is here, right? You're saying that the middle post was taller?
Yes, it was the same height, but it appears taller when you sight. And this is basically if you take this drawing and you turn it upside. Yeah, this is the best drawing. This is not exactly what they saw through the telescope. The previous drawing you showed 5 seconds ago, that's what they literally saw through the telescope because it's inverted. It didn't have an optical correction, so we are literally seeing the bridge upside down.
Right.
But the bottom line is you have a horizontal line which is level. You have I guess it's 2 discs they had. And then you have this black stripe, this black horizontal stripe. That was the banner, the one marked number 1. That's the banner on the far bridge. And then you have 2 discs. The higher of the discs was marked number 2, and that disc was literally 13 feet above the water, as was the banner, as was the telescope. So if the Earth were flat, it would have been a straight line from level line to disc number 2 to banner number 1.
Now you have to read.
Okay, it would have been all level.
But he describes it in his book. That's why I'm confused how you don't understand.
Yeah, he explains it away because he was a true believer. He genuinely believed the Earth was flat. So he sees evidence right in front of him, and he explains it away. I mean, but that meant he's sincere. He was sincere.
You have to have the disc that's close to the telescope, meaning you start the telescope, and then you need to have a disc right in front of you, also 13 feet high. And then you line it up with that.
Yeah, well, but instead of having that first disc, I mean, like, right there, you just drop a tape measure to the water, and you find that your telescope is the right height. I mean, that's, it's almost like a virtual disc.
How you don't get if you have a telescope at 13 feet high, and you lock it in right there, it's level with where you're at.
Yes.
Right. If it's looking off in the distance, it's not going to hit the horizon line. Right?
Well, yeah, but the flat Earth argument is that the horizon rises to eye level. So according to the flat Earth, it should hit the horizon line. According to the globe Earth, the horizon will be, oh, I see what you're saying about 13 feet up. Okay. So, but when you look 6 miles away, I mean, how big is 13 feet? It's a thousandth of an inch, so your level line 13 feet above the canal, I see what you're saying, but it'll be proportionally 13 feet above the water, but 6 miles away, that's measured in arc minutes.
So here's a way to describe it. Let's say we're standing on a completely flat ground. Okay. Now we're saying it's flat. And there's a railing that runs, it's 3 feet high. The railing runs off into the distance, stays exactly 3 feet high the whole time. And you stick a telescope on top of that railing. So it's just laying on the railing, looking in the same direction the railing's going. And at the end of that telescope, will you still see the railing, or will the railing have fallen below the telescope level line?
Well, if the telescope is resting on the railing, it's kind of unclear as to how much of the railing you're going to see. I mean, it's just going to but it's going to be level. It's going to be level with the telescope. It's not really going to drop away. If you had a 6 foot high telescope,
because the telescope is only increasing your view of what's seen in the telescope.
Yes.
So it can't go down or up.
Right. But it's kind of hard for me to understand the picture you're trying to paint of the telescope, like right there on because the telescope is right there on the railing. It's the railing is going to fill up half the viewfinder of the telescope.
Correct.
It's going to, it's just going to be this mass, this blob. I mean, you're not really going to see a crystal clear railing because you're right on there. But
because I think this is important, because I think this is one of the major things that people are having trouble with. So you're saying if we have a telescope, sorry, I'm just gonna take a second here, and
fat telescope.
Yeah, just reduce this a little bit. Okay, so we're looking through the telescope, and let's say that it's sitting on that railing. Okay, so there's a railing that's here. Can I get the right color here? Yeah, yellow. That makes sense. Okay, so this railing is here, and we're looking in the telescope down the railing. Now, at a distance, we know this telescope's going to go down, right? I mean, this railing, because we're looking. It's hard to
a
draw.
6-foot observer, right? But I mean, it almost is going to look like the railing is going to go up because everything is going to kind of merge into your horizon line. I mean, the line is the horizon rises to eye level, but I say that's not entirely accurate. I say the eye is drawn to the horizon. But if you're just a 6-foot tall person and here's a 3-foot tall railing, that railing is going to go. It's going to meet that horizon line. Okay, so basically extend that yellow line up, but only halfway.
Okay, so if we're sitting on the railing, okay, you're right.
Yes.
You're saying that you would see the railing right here, right?
And I gotta wrap this up in at least less than 10 minutes.
Okay,
I promised my wife like 30 minutes ago that it would be 10
gotcha.
minutes.
Okay, so what I'm saying is this telescope view. This is all the telescope can see. Okay, so when you zoom in as far as you can on the telescope, you can only see this circle.
Right. But what I'm saying is that the railing, if you extend that yellow line up to the horizontal line, the railing is going to fill half of the viewfinder. It's going to go up to essentially the railing is going to disappear into the horizon.
Yes.
So the yellow is going to go up and it's going to stop at that horizontal line.
You don't think it'll stay below it?
No. I mean, it depends on how short the railing is. If it's a short railing, sure. But if it's a really long railing, and we're on flat, and when we say flat, we mean like construction flat, not sea level flat.
Mm-hmm.
All right. Then it would go to the halfway point. It would basically the railing would disappear into the horizon, and the horizon is that horizontal line.
Okay, that's something I think that I can actually do.
Yeah.
So
well, here's what I'm going to say, Jaron. Can we table this part of the conversation because I do have to go, and it takes some time and make some drawings, and maybe I'll make some drawings and something like that. But
let's come back and talk about that, because I do think that Robotham experiment is a big deal.
Okay.
And I think that if we could get to the bottom of that, that'd be good. So I do appreciate you joining me.
Oh, yeah. Thanks for hosting, Jaron, and thank you for all the listeners. Thank you for your patience. I know this was a 2.5 hour, a little bit longer hangout. So I do appreciate the patience, but hopefully people got something out of it. And thank you again for hosting, Jaron. I appreciate it.
I didn't get to show you the moon thing. This is all I wanted to show you before you go.
Oh, okay.
So this is real in your mind, just so we know that. This is the Japanese Selene orbiter, and it's going through the moon. And when you see the Earth rise here, I'm going to show you that, and then you can be done. Yeah, here's the Earth rise. This is supposed to be real. Okay, this is not animation. This is really an orbiter that's going around our moon, and people wonder why I don't believe in cosmology and all this nonsense. Wait till you see this Earth rise. Get a little further. Come on. It's going to come up here. Here we go.
Okay.
Now, you think you live on that ball, and you think this is a real video of an orbiter going around the moon. This is being sold to people as real, Charles.
Well, if you look at the shadows in the near craters, how it's clear that the camera is like, if you back it up a few frames, you see that we are clearly on the sun is exactly at our backs, right? The sun is exactly at our backs. I mean, literally, if you were to back it up like 30 seconds, the sun is exactly at our backs. You can't even see the craters. You just see bumpy land, right? I
mean here.
Right. You don't see a single shadow. You know why? Because the sun is exactly behind us. So that when the Earth comes into view, is it any surprise that it is a full Earth?
No,
because the sun is exactly behind us. So see, you could say that looks fake. Okay, I'm going to give you that. It looks fake, but lots of things look fake if you don't understand the details. So yeah, I mean, if you want me to say, does that look fake? Yes, it looks fake. But is it fake? No, I don't believe it is.
You don't believe it's fake?
Nope.
You think?
I mean, take a look at the quality of the shadows. Do you see how the shadows are lengthening? Because we are going around the moon. The sun is no longer at our backs. The sun is now below us, behind us. Okay, so the shadows are starting to get longer. We are clearly above the level of the light source, right? I mean, the only way you get that lighting is if the sun is below us, behind us.
New
But anyway,
things.
Anyway, yeah, it's just
Right.
ridiculous.
Yeah.
Anyway.
but we will talk about some of the stuff later. I do appreciate your hospitality and inviting me to come on to talk about 5 things we should have been taught in school. Yeah, and I hope everybody has a great evening.
All right, guys, I appreciate you guys watching, and we'll talk to you soon. Thanks, Charles.
Okay, goodbye.